Now can you hear me? Oh, yes, okay. So it's not using the microphone we have, but the computer one. Hi, good morning. Okay, so let's begin. Good morning, everyone. I'm Ehud Barnea from Drax, and I would like to welcome you to the third RetailVision workshop. Now, the last 2 years were virtual, so I'm really happy to be here today with you physically. First, I would like to thank everyone that made it happen, the speakers, the audience, my co-organizers from Alibaba that unfortunately could not travel to CVPR today, and a special thank you goes to Lee Hizanik Manor. Now, about the workshop, computer vision has been transforming the world of retail in the past few years, and it will continue to do so in the future. Now, the beauty about it is that we have computer vision for physical retail and online retail, but now the physical and online also interconnect. So the goal of this workshop is first to present the latest work of computer vision in the world of retail, and then to also advance the research in the field. Now, usually without proper data set, it's very difficult to do research. So with our challenges, we enable anyone to take part. Now, I'm also happy to announce that this year we actually had more than 1,000 teams participating on the Alibaba Recognition Challenge. Just a brief overview of the workshop. So first, we're going to have several talks about online retail, and then several talks that are more about physical retail. Now, we're going to have a long break, and then later a short break, and we should finish at 1 o'clock. You can find the complete schedule at the workshop website, as well as the challenge winner reports that will be uploaded today or tomorrow. But we'll also have them speak here today or present videos. Now, this is the first hybrid CVPR, and while it's kind of cool, it's also quite difficult. So we're going to have physical talks, recorded talks, and questions over Zoom for the recorded talks. Now, all the workshops will be recorded and then shown next week at the CVPR website. And then 3 months from now, they'll be shown for everyone, even without registering to the conference. Now, be it as it may, it's quite a difficult setup. So I hope that everything works okay, and we'll have a great day. A few words about the challenges. Drax is the market leader when it comes to supermarket shelf digitization. We go to long supermarket aisles. We take many images that we then stitch together to a single image in which we recognize and detect basically anything on the shelf. It can be products, prices, shelves, you name it. In the last 2 years, we had 2 challenges based on Drax's real-world data. We had dense product detection, and then we had product pricing. Alibaba presented the recognition challenges. So in the last 2 years, we had product retrieval based on product images. And then this year, we had multimodal challenge with both product images and textual captions. Now, the challenges in this field are many. We have fine recognition, long-term recognition, and also new products or new classes that join every day. They will talk about it more later on. Now, before we begin, it's important to state that today is the Juneteenth holiday, today and tomorrow. And this is the day where they celebrate here in the United States, the end of slavery. And it's a very special day, especially here in the South. There will be local events around the city, and especially a notable one at Louis Armstrong Park, which is a short taxi drive away. So you're welcome to join it after today's workshops. So that's it for now. We'll now have the talk by Michael Black, which will be then followed by questions with him over Zoom. Okay, so thank you.
Talk about RetailVision.
Hold on.
This workshop.
Okay.
Hi, folks. I'm Michael Black, and it's my pleasure to be here today and talk about RetailVision at this workshop, and I'm sorry I can't be there in person. It's actually the first CVPR I've missed in 30 years. Really wish I could be there with you and enjoying New Orleans. So, but my video presence will have to do. Unfortunately, I'm not yet an avatar, so you're going to have me in real life, real recording here. But I want to talk about some work in my group on avatars and what I think that means for meta-commerce. Now, maybe meta-commerce isn't a term that a lot of people are familiar with yet. We all know regular old commerce. So there's women buying some clothing in an actual store, touching it, trying it on, etc. And we're all familiar with the e-commerce version of that, which is kind of a poorer approximation. I can't touch things, I can't try them on, I don't know if they're going to fit, and a lot of people don't like buying clothing this way. So what's meta-commerce? Well, of course, it implies something about the metaverse, and what will commerce be like in the metaverse? So this is an example from Instagram. It's a partnership between Forever 21 and Roblox, the video game, and Roblox has been a pioneer in metaverse kinds of applications. So what you see here is a woman who is wearing various clothing from Forever 21, and her Roblox avatar is dressed in the same clothing. Now, this is something that's called twinning. You have a twin of your clothing in the real world and your clothing in the virtual world. So what's important here? Well, there's a number of things in this very early video of what meta-commerce is going to be like. But there's the key things are really a blurring between the physical and the virtual. So this Roblox character appears in the real world in a augmented reality kind of way in the apartment of this young woman. And the avatar and the woman, even though the avatar is obviously not designed to be a physical likeness of her, they share various characteristics, hairstyle, overall build, maybe facial shape, and a few things like this that connect her with her avatar. The customer and the avatar are wearing the same clothing. And the interesting thing here is, of course, you can buy this clothing in both physical and digital worlds. And in fact, there was an interesting crossover. People were selling, Roblox was selling Forever 21 beanies, and then they were so popular that Forever 21 made them in the real world. So people could buy them and have them in both the real world and on the virtual character. And this is the real exciting point, I think, for meta-commerce. And one thing that's key here is that 3D avatars are playing a central role. Okay, so the game character here is not a very realistic avatar, it's 3D, and that's important because it can be embedded in the 3D world of the owner, in a sense, of the customer, blurring that boundary between the physical and virtual. And there's another key thing here, which is that it's designed to be a fun experience. So these are, I think, some of the unique principles of meta-commerce that distinguish it from the previous e-commerce phase that we've been in for a long time. So I argue that this age of avatars is coming, and what do I mean by that? Well, I mean that the avatar will be everywhere and a key enabler of the metaverse. Now, I have to define for you what I mean by avatar, of course, but people mean all kinds of different things, from fun Roblox-like game characters through to fully realistic digital twins, replicas of a person that are fully real. But I think it's neither one nor the other, it's all of those. People are going to want all kinds of avatars for all kinds of things. They're going to want maybe a fully realistic one for digital fashion and fitness and health applications. For training AI algorithms, we want synthetic data that's fully realistic. But in games and entertainment, we might want to choose other kinds of more fantasy or cartoon-like characters. And then in augmented and virtual reality we can do whatever we want, but in augmented reality, we also have to kind of connect with the physical real world. We may want to augment our bodies with the bodies of other people. So that ties us to this physical realistic. It's got to move like a real person. It's got to interact with other avatars in 3D scenes, maybe in an augmented reality case in the actual 3D world. It has to plug and play across these applications. It's not, the metaverse is not going to work if everything is siloed in your digital fashion avatar doesn't play well with virtual reality or your fitness app or your games. Right? There needs to be a common kind of platform so that all these applications can talk to each other. You know, imagine if the internet if it was siloed into different areas. And so it has to, the other thing is it has to work with your graphic systems today, whatever we build. It's great to think about the future, and we definitely should, but people want these things to work now. So the problem for doing this is there's just really too much friction. It's time consuming to create an avatar. These avatars aren't portable. The whole process doesn't scale. So what we've got, one extreme, we've got things like 3D scanners, which are accurate but expensive, and who has them? I have one, but I have several, but most people don't have any. You think, well, maybe these LiDAR scanners on phones are solving the problem, but if you ever look at the data, it's actually pretty noisy again. It's very hard to scan a whole body, for example. So most creation methods that try to create a realistic avatar use some kind of video capture app on your phone, where you type in clothing and take a pose and move very carefully and follow instructions. It's not the kind of thing you can do in your cubicle at work. You have to have the right clothing. It's time consuming, and users don't really follow instructions. They never listen or read. So the whole thing doesn't really work very well. It's a big barrier. And so most of the time, the avatars can be great, or these sort of fun, goofy, unrealistic things where you can pick your hair color and so on. And that's where we are today. I don't think that's where we're going to be in the future. I think we're there today because that's the low friction way of creating avatars. So what we really need is a low friction way of creating your digital double, something much more like you. And so just some example of work we recently published at 3DV called Pixie, which takes an image of a person and reconstructs their 3D body, their facial expressions, in relatively good detail, really captures those hand poses and something expressive about the body. So that's what we like to move towards, but even better. And the foundation for all of this is a 3D virtual human. So what's a 3D virtual human? It's a simple mathematical model of body shape. It should look like a real person. It should move like a real person. It should be compatible with standard graphics tools, so it's portable across all platforms. It should be able to interact with people and scenes, so it should have facial expressions, gestures. It should be able to contact the world, the virtual world, and it should also model clothing that we're not showing. So, for several years ago, in 2015, we introduced a model that's become popular called Simple, which is a skinned multi-person linear model. Many of you probably are familiar with it, so I won't go into details, but the basic thing is a function app that takes pose parameters theta and shape parameters beta, and it uses it's portable because it uses linear blend scaling. W is a linear blend scaling function, common in graphics. It takes some arguments and produces vertices of a watertight mesh. The arguments it takes is a template mesh, which is a function of body shape and pose, some joints, which are a function of body shape, some blend weights, which are learned and pose of the body. And this whole, the key of Simple was, well, one, it was built on linear blend scaling with these little additions, but the key thing is that everything was learned from thousands of scans of real people. And that meant that it could really be accurate and model the body well. But the problem of really capturing humans and in all their glory is a challenging one, because humans are complicated. We have varied body shapes, for example. We wear complicated clothing in layers. We move in complicated ways. We gesture with our hands. We emote with our face. We communicate with each other, to reveal something about ourselves that's important. We contact our bodies in ways that make computer vision challenging, but for support, self-support, and also to communicate. We interact with objects in the world, a huge variety of them, and we don't just grasp them with our hands, we use our whole bodies to interact with objects. And we don't just interact with objects, we interact with each other through social touch, handshakes, and hugs, and kisses. So understanding human bodies and their interactions, and then recreating them in avatars is a massive challenge. And I won't solve it for you today. But I'll take you on a little journey of where we were and where the field is now. I'll blatantly plug a few CDPR papers that we have so that you can check them out. So I think the first breakthrough in estimating an avatar from images really came with Anshu Kanazawa's work in 2018. And this is classic now. This is how many things work. You take a cropped image region around a person that goes into some encoder, ResNet. There's a neural network that then regresses pose parameters, shape parameters, and camera parameters. Cameras just scale and translation perspective, so that varies. And then it outputs the parameters of a simple model using that function M. We can reconstruct a 3D body, and using the function J, which takes the body parameters, takes the joints, we get the 3D joints of the body. And then those get projected into the image, given the camera, and then we get 2D joints. Now, there are lots of data sets in which people have gone through and labeled the 2D joints in the image, so one can just write a simple L2 loss on the difference between the observed 2D training joints and the projected ones. So you can minimize that. And by the way, Anshu's, one of her key insights was to iteratively regress these body parameters. But anyway, if you just do this, you end up with what I call monsters. You get body shapes that really don't look like the person in the image, even though they minimize this 2D joint error. Right? So that didn't work. And so Anshu had another great idea, which was to use discriminative training. So here we have a data set of lots of people. We know a lot about body shapes and poses. So if the regressor produces a body that doesn't look like a body that we know to be a true human body, then the discriminator will learn to detect that and reject it. And so training this all together, the network actually produces good results. So that's all the way back in 2018. Where are we now? So I'll just give you some teasers for current work. So we have a paper called DEF, which stands for Bird's Eye View, called Putting People in Their Place, Monocular Regression of 3D People. So Yusun is the brilliant student who's been doing this work. And the whole idea is to break away from this idea of detecting bounding boxes around people and then processing all the bounding boxes in a multi-step paradigm. Instead, we just want to process the whole image at once, and we want to estimate all the people in the image in one shot and put them all in depth. And we want to do this all, train this all end to end, and we want this to work regardless of the age group in this picture. So here we have kids and adults. So the previous methods, this is just an example from Vive, all do bounding box detection first, find all the people, and then process them. In cases where people are overlapping, however, things can be really ambiguous. The other thing is when you crop out these bounding boxes, you no longer get to see the whole scene. And so you lose all the scene context that can tell you a lot about what's going on. So these methods tend not to be very robust, and they're completely dependent on the bounding box person detector is. So we've been focusing with a couple papers, ROMP and Dev, that are simple one-stage frameworks. ROMP is real-time, it estimates all the people in the scene, and it's robust to occlusions. So here you see some examples in the back dotted boxes where the bounding boxes have a people including each other, and these end-to-end methods do that there. So just briefly, what did ROMP do? This was from ICTV last year. ROMP takes the whole image in and then has these 3 heads that produce different maps. The first one is a body-centered heat map, which basically is telling you the probability that there's a body centered at a particular place. And you see little heat maps there on the top. And then there's a mesh parameter map, which basically says at each point in that body center map, if there's a body there, what are its simple shape and pose parameters? And so we store those there. And then there's a camera map. And then you can sample from the body center heat map, get bodies, and then with their simple parameters at every image position, and the image with the camera. Now, that worked pretty well, except that center heat map is a heat map in the image plane, and it doesn't know anything about depth. And so ROMP doesn't do a very good job of putting depth, as you can see on the left here. And another recent method, CRMH, also has problems if people are the wrong size and they're the wrong depth, even though it reasons about that. But then we introduced an explicit 3D representation. Now, doing inference in a full 3D representation is complicated, so we have a trick for dealing with that. Another problem with existing methods is they all use a simple body, which is just for adults. And if you see a child in an image and you assume it's an adult, then it's a very short adult. So the only way to make that plausible is to make it a regular size adult, but put them far away. So and so that's exactly what you see here with ROMP and CRMH. This lineup of kids, from small kids to teenagers, you see that instead of being in a straight row, they're all slanted in depth. But Bev estimates infants, children, teenagers, and adults, and manages to figure out that they're all just different ages. So how does this all work? The first trick was to begin reasoning in 3D. So remember, ROMP takes in an image and creates a center heat map aligned to the pixels in the image. Well, with that, we introduced an imaginary bird's eye view. Just imagine there is some cameras. We don't have it. We just have the front view. But imagine you had a camera looking down, which would look at all where the people are. You could also try to estimate the heat maps from above. And that would put the people in depth. And so Bev is going to try to do that. It's going to try to estimate the front view and this bird's eye view that it doesn't see. Now you might say, well, you could just estimate all of this in a 3D volume, and we did try that. It's a lot more parameters, it's a lot more complicated to train, and it doesn't converge as well. So this is putting the idea that these are separable representations. And the other key idea is to use a weakly supervised training scheme. And we do 2 things there. We introduce training data about ages of people. We also introduce a version of symbol that can represent infants, children, and adults. And we also have a loop labels on depth ordering that we exploit during training to train the method. So just quickly taking you through that, the way that works, it takes the input image. It looks a little bit like ROMP here. We have the body center heat maps. There's offset maps, there's a refine map, and then a mesh parameter map. And then what we add is this bird's eye view representation, as well as offset maps for the bird's eye view. The front view and the bird's eye view can then be composed into a full 3D representation. And then we can reason about that 3D center. But training it this way works better. There's also a camera map, there's a like ROMP, and a 3D offset map. These things all get sampled from, allow us to estimate the translation of people in depth. We then can sample the feature map, and we can do the depth ordering, and put the body shapes in depth. And the losses we use here, there's a L depth is this weak depth ordering loss, and L age is this loss about the ages of people in the training set. And for people of different ages, we have ranges of their possible heights. So to train all that, we needed a data set. So we've created this relative human data set that supports in the wild and not here. Depth reasoning is weak annotations with depth layers here. This sports team, frisbee team, the blue people are in front of depth layer 0, the yellow are in depth layer 1, and then there's a guy in gray and yet another depth layer. And so this is just a weak labeling of depth layers. And then we also, here on the right, there's an image in which the people are labeled in the depth layers, but all in the same depth layer, but different ages. There's a, it says teenager here, there's a child, a baby, and an adult. And then we design losses to take into account these things and expand it simple model. So let me just show you some results. Here's an input image, CRMH estimates a bunch of adults, so it gets the children wrong and goes to depth ordering wrong. Wrong also does the same thing, it's different depth ordering, but Bev actually does something sensible with the children and the spatial relationships. We don't have any reasoning about it. A few more examples, people lined up. I like this one of the royal family, because you got a bunch of ages, and the spatial relationships are roughly right here. So crowded scenes like this, again, there's no bounding box detection here. It's just a one-shot method that produces all the bodies at the same time and the depth relationships. Here are different ages again, and correct depth relationships. And this one is on great scale images from the old days. Anyway, so that's where we are with estimating people from images. Now, there's something really missing here. You'll notice that the body shapes, apart from now we can deal with ages a little bit, they're all pretty generic bodies. Basically, the current state of the art, most of the methods estimate something like an average body shape. So we have another paper here called Shaky. This is the very first talk of the conference in the very first oral session, so please don't miss that. It's on accurate body shape regressions, semantic attributes. And the idea here is, for many applications, particularly in the retail space, we want accurate body shapes. And we want to reduce friction. We don't want people to have to go to scanners and have lots of measurements. So how do we do that? Well, if we had paired data of images in the wild, like the image on the left, people in arbitrary clothing, and we had ground truth 3D body scans or simple model parameters, then we would just have a supervised learning problem. We could train a network to regress from images to 3D body models. But getting paired data like that at scale, given the variety of people and clothing and so on, it's actually, that's a non-trivial task. So we asked the question, what could people label? I showed you that the original work was on Jew, the HMR method, used hand-labeled key points, 2D key points. Humans are good at that, they put it on points. What can people do about shape? Well, they can't tell us, how much someone weighs and exactly what their waist size is. They're not good at that. But we do have words that we can use to describe shape. So our question was whether we could use linguistic description of shape to capture the body. And this idea we explored in some earlier work, SIGGRAPH 2016, on a piece of work called Body Talk, where we showed that people do use language to communicate shape. And this means that we have in our heads some mental model of body shape in 3D that we can use to communicate. And here, the model learned various things like, for women, various words like feminine, long legs, pear-shaped, rectangular, round apple, and short were associated with these sort of prototype bodies. And we built a mathematical model. So our idea was, well, maybe we could use that same idea to train a metrically accurate body shape regressor using only linguistic descriptions of images. So that's what we're going to do. We're going to take images like the one on the left and have them rated by a bunch of workers on mechanical turf according to a variety of phrases like pear shaped or muscular. And then we're going to formulate a loss that helps us train. So to do this, we have to label two different types of data. We label 3D bodies, like the one on the left, which we have lots of different body shapes from the season data set. They get rated on 15 of the top shape words from body thought. We average the ratings of the raters. We also have the raters label image data, like the one on the right, with the same words. And they're not paired, right? We don't have the 3D scan of this woman on the right. It's completely separate data sets. It's a scan data set and an image data set, but labeled with the same semantic shape words. We do a bunch of stuff, and I refer you to the paper and the poster for details, the oral as well. But a key thing is something we call shape to attributes, or S to A. Given a body shape, say we regress this person's body shape from the image. Given the body shape, we train a very simple polynomial regression model to take the shape and predict the ratings that correspond to that shape. So for example, this person has broad shoulders, they do not have a delicate build, they have a long neck, they're masculine, they're muscular, very muscular, they're not short, they don't have a soft body, okay? So we train that on this standard, this shape to attributes. Now, shape to attributes turns out to be a key player here, because what we're going to do is we're going to train a regression method, a little bit like the old Drew method, except we're building this on top of exposed, so familiar with ours. We take an image in, we train a regressor to predict simple X, pose parameters, and simple X shape parameters. We take those shape parameters, we pump them through this polynomial model shape through attributes that gives estimated attributes for the regressed shape. And then we add to our loss, or standard training loss for 2D joins and all of the other stuff we just normally do here. But we add a loss on the attribute values. The attributes of the estimated body shape should match the attributes that were labeled for this image. And that turns out to be enough to predict body shape, to basically ignore clothing, and to do this at the state of the art. So it turns out that if you have carefully controlled imagery with textual clothing, you could do better also by excluding silhouettes. But if you don't have that, if you have sort of images of wildlife, methods that use silhouettes get very confused by clothing, and this approach shaped this really well. But I'm going to argue that we need even more if we want to be able to control our avatars and really feel like we own them. We need them to be emotional, and for that we also need to capture the emotion of the users who are controlling or using their avatars. And for that we have a paper called the MoCA, which regresses 3D faces directly from input image. It's robust, and the clever idea here, I think, is that it uses some side information. It's trained completely from images to estimate the 3D flame parameters, as well as detail parameters, detail shape. And what it does is it exports information about emotion for training. This is a poster on the 24th, in poster session 4.2, in MoCA, emotion driven, not for face capture. And check that out. MoCA is based on a method called DECA from SIGGRAPH 21, in which we have taken an input image, we encode the shape, the expression, and some detail. We estimate the albedo and the shape, we combine all these things, we differentially render that, and we produce an image, okay? And in the standard, we have standard losses in DECA that, look at how similar that image is to the input image. The novelty in MoCA is this top bit, which is we add an emotion consistency loss. And that says, if we take an emotion recognition network that detects the emotion, the valence, and the arousal in that image, the emotional content of the input image should be the same as the emotional content of this rendered image that we are generating from the model. And so we formulated a motion consistency loss that encourages that. And the result is that this EMOCA method learns to produce much more emotional traces than DECA or the current state of the art. All right, I'm really just about out of time. I think I have 5 minutes left. So all that's well and good, but there's still a problem. We've been working with these simple body models, which don't capture things like hair, clothing, shoes, and other personal details. So to really, we're going to want these avatars like that case of twinning I said. We're going to want to dress them. So we need something that's richer and more visually expressive. So we have a few papers here. I'll just point you to. GDNA is a generative model of 3D clothed people. We have a distribution over people that we can sample from. We can pose them and change their body shape with simple parameters. They're not super realistic yet, but this is the first generative implicit model of clothed humans. So I encourage you to check that out on the 24th implicit session too. Now, we have another paper on trying to create more realistic looking avatars using implicit representations of shape and texture and so on. And here's, this is work, this is an oral on the 23rd at 1:30 session in the afternoon. It's called I Am Avatar, implicit work with head models. And Otmar is one of the collaborators, so he's talking about it. I don't know if you can hear. You can get really hear us, right? He's saying that I Am Avatar is great and it's the best thing in the conference. And so this is from a very short video clip. We construct a slide on it. For a very short video clip, we construct an implicit model that's really it's like linear landscaping used in 3D MMs for the head. But we replace all of the pieces with continuous fields in a canonical space. So there's canonical continuous fields for geometry, texture, deformation of bone shapes, and linear landscape grids. And behind this whole thing is the flame head model parameters, so we can actually control the head with head rotation, jaw pose, and facial expression parameters to generate new heads and even extreme poses. It's all one video. And then finally, we want to really create full body avatars from images, and we want to be able to do it from arbitrary images and arbitrary poses. So here, there's the results of Icon, which is on the 23rd in the morning, post session. Papers on implicit clothed humans gained from normals. The blue is the rendering from the front, and the bronze is the rendering from the back. And you see that there's some pretty extreme poses here. So we can take images like this, where current methods fail, and methods like HaiFu and Arch++. These are great methods. They work really well on fashion images, fashion posts. They don't work well on these kinds of poses. But Icon does a reasonable job of reconstructing 3D shape from a single image of a person in clothing in crazy poses. So I think this is, and from this, we demonstrate that we can actually build an animatable avatar. It's not perfect yet, but you get the idea where we're going. We're trying to exploit the latest in implicit and neural rendering to create much more realistic avatars. So where's this headed? 3D avatars, the age of avatars, as I said at the beginning, is definitely coming. It's going to have a big impact on how we shop and how we play. Reducing friction and creating these avatars is key. We want to be able to animate them with user motions and facial expressions. This is what builds a deep connection with the avatar. They need to look more realistic than the ones we have today. They need to have clothing, shoes, accessories, and look like real people. And implicit surfaces, neural rendering, radiances, etc., are all progressing very quickly. Some of them have worked well for rigid scenes and are being extended to articulated and formable objects like humans. So that's coming very quickly. easy to make, easy to create, easy to control. It's you, only better, because you don't have to be here. So go get your I am avatar and get it. So there you go. That's not even me. It's my avatar talking, and hopefully it sounds believable. Thanks everybody for your attention. I'm happy to take questions.
Okay, so let's see where we are.
Can you folks hear me?
Yeah.
Super.
So does anyone from the crowd or even online would like to ask a question? Maybe you can try talking to this microphone.
Okay, sure.
I'm not sure it will work, but let's see.
Okay. Hi, Michael. Do you hear me okay?
Hi, I can hear you.
Okay. First of all, I would like to thank you for the great presentation. Second, this is a very hot topic, especially in modern e-commerce. And out of curiosity, can we overcome the problem of precision in terms of 3D image generation by using multimodality? What I mean by that is, as you know, sensors are getting smaller, more accurate. For example, Apple recently embedded a LiDAR sensor as part of the iPhone offering product, especially for the iPhone 12 Pro and the Pro Max, and it's laser-based. We are beyond the limitations of the light-based ranging and detection. Out of curiosity, instead of trying to put together multiple blocks and try to predict everything from nothing on limited data, can we like merge LiDAR data, cloud point-based, sensed through laser pulses and 3D imaging to improve or speed up this entire research field? That's my question.
Okay, I heard that, I think through the not the microphone you were using, but through, so I got bits and pieces of it. Let me see if I got the gist right. All kinds of small, lightweight sensors coming. They're going to be on phones. They're going to be sensing depth. That could really speed this up and make it a lot easier. Is that roughly right?
Yep. Yes.
Super. Yeah, absolutely. My feeling is those things are not yet really here. From a research point of view, sure. You know, we have fancy scanners in the lab. We could do all kinds of stuff. I'm interested in what we can do with the tools people have today in their hands. And so that's mostly RGB sensors. What do you have stored on your computer in your photos folder? Right? It's RGB photos. What can we do with those things? Maybe we don't need these fancy sensors in the end. I don't know. If we had them, yeah, and they really work today, we would probably use them. But I'm also really interested in what you can do from, say, archival video, from a TV show. Can you reconstruct all the characters? And even if you gave me perfect scans of people, there's still the question of how do they behave? How do I model their movement, their facial expressions? How do I get at their goals and their intentions, their interactions with the world? These are all still hard problems. And those aren't answered by better sensors particularly. So there's still a lot of fun ahead. Are there other questions?
Any more questions? So I'd like to ask one. Not entirely related, but this makes me think about the concept of the uncanny valley.
Mm-hmm.
So it makes me think as if the avatars somehow overcome this problem. It's not present to them. Like, what do you think about that?
Yeah, it's a great question. And I think it's one of the reasons people have stayed away from realistic avatars.
Mm-hmm.
But you saw the video of me at the end. Okay, it's a bit grainy, and it's not the resolution I would like. But I don't get an uncanny feeling from it. It really does seem like me.
Yeah.
And I showed it to my wife, and she was like, "Oh, that's you. It's really you." So I think we're getting there with neural rendering techniques and deep learning. I think we're crossing that uncanny valley, and it's not just about visual appearance, it's about movement. Movement is really critical. This little subtle facial expressions and body gestures are key. So I'm quite hopeful that we'll build a bridge across the valley.
Thank you.
You're welcome.
Thank you. Just another one, you were talking about the attributes earlier. I was wondering how you annotated the attributes because it seemed like they're continuous values.
Yeah, so we have the raters are given a 5-point scale. They see a word like hourglass, and they have to say, do they completely disagree, agree, neither agree nor disagree, you know, etc. on a 5-point Likert scale. And then we actually average those ratings. And we've tried not averaging them. We've tried using the raw values and the average values, and it works better with the average values. I'm not sure why. So that's where you get the continuous number from. And we've tried all kinds of different ways of regressing from those using an MLP and all kinds of things, but averaging the values and then a simple polynomial regressor was the easiest.
I think, thank you. Any more, maybe from online? By the way, were you able to hear the talk from online?
It wasn't great. I think it was playing through your laptop mic or something, so it was a little hard to hear. I think if you share the screen, you can click, you want to share it with audio, and then it would have been clearer. I'm not sure.
Yeah, thank you. We tried before and it didn't work, but we can now try again.
Okay.
Okay, so thank you very much.
But I could hear it.
Cool. So we'll try again for like 2 minutes and then we'll continue. Thank you.
Thank you. My pleasure.
לא, אתה יכול לעשות את זה?
Extension. Is extension from American to Europe?
No. Not giving you good context.
Yeah.
No. Can you try it? Nice. Thank you. Okay, and now let's see about the audio. This mic?
Yeah.
And to like hold it? Oh, well, it's taped, so I wouldn't try to touch it. Oh, nice. Of course. Yeah, I guess you could. But then we need to make sure that the input comes from here. So let's see. Can you confirm one? So looking at that, it seems that the microphone is not like this is not recognized as a microphone in my system.
No, it won't be.
It won't be.
No.
Okay, so is that okay or?
Yeah, it's using an internal microphone over Zoom.
Okay.
But it should be hearing whatever's playing in the room, whatever's you're speaking on this microphone, whatever's going on in the room, this laptop will hear it. So that's the best we can do. I have another set of microphones that I want to set up, but in the middle of the show, I can't do that, and they need to be charged.
Yeah, so
But the thing I do want to change is the output of the audio from Zoom from that to the surrounding room.
the output. Let's see. So is this
Oh,
not
we
the
have
right
to go into
speaker?
settings.
Audio settings.
Oh, yeah, oh,
Okay.
just saw that back there. Built-in headphones.
Okay.
Now, if the Zoom says anything, it will come through here
Mhm.
and go through the audio in the room.
Okay, great. So the next talk is physical, so it should be better. Then during the break, we'll have more time to see things. So now we have Yossi Keller, a professor from Bar-Ilan University. We'll talk more about e-commerce.
Thank you, El.
Thank you. Let's
Yes.
just,
Control L on Windows, but
no, not on the Mac.
I'm not hinting that there is an issue. Full screen. Yeah. Thank you.
Okay, so please
Let's
try.
see that it works. Okay, we can start. Okay, so good morning, everyone, and I would like to use this opportunity to thank the organizers. As I will discuss today, I do believe, and you take it, I do believe that machine learning and e-commerce are actually coming together and it's becoming more and more important than it used to be to apply machine learning. I will discuss specifically a particular aspect of multimodal image text embedding that we worked on, both in the academia, publishing some papers, and then had our own startup last year, and we spent about 10 months about understanding how to utilize that in the e-commerce environment. And it's interesting to say that in Michael Black's fascinating talk, he also mentioned using image and text together. If you remember some of the examples we did about using some semantic notions into the shapes. So, yeah. Yeah. Worked until now. Yeah.
For the full screen.
Yeah.
Let's see.
Can I sing?
Try now.
Okay. Okay, thank you. Thank you. So that's our first paper. It's available on PAMI. It was accepted like 2 years ago. It's open, but not any publication. There is a long queue. And then that's a new thing that I will discuss today. And the e-commerce part, I'm trying to share with you some of our insights about how to utilize multimodal text image embedding in e-commerce. And I'll just give you a very simplified overview of the e-commerce system. It's really simple. There is one equation you have to remember. It's a combination of CVPR and CNPC, both machine learning and both economics. You have to understand that once you move into real applications. So the system is built of three parts. You have the customers who want to buy products. They can either go directly to e-commerce sites like Amazon, Alibaba, Zappos, whatever, Nike, all of those. And this is typically true for the large dominant brand. Most of the sites on e-commerce actually don't know them. Might be fine for them, but they don't know them directly. And the way to get to them is through advertising and targeting. That's the business of Meta and Snap and Twitter. Okay, so many media platforms that do that. And this particular path is shown to be very efficient. So also the other ones like Amazon, Alibaba, the brand names are actually depend on advertising and targeting. So they get part of their customers to here, but then most of them come for advertising and targeting. And the most important part of our e-commerce view is the SMB, the small and medium businesses. So those are the businesses that sell up to $50 million on average. But you'll never know about it. So Peloton used to be an SMB, it's not an SMB, it was much larger. So the way they got name recognition was through advertising and marketing. So that's the system. And I'll show you today that actually here inside the e-commerce side is well actually lack most of machine learning, in particular in dual dynamics that I'll discuss today. Yeah, so just to give you some number, nowadays 75% of Amazon's revenue comes from free e-commerce. Not through services, not through AWS, no. That's the bread and butter of Amazon. Meta, 98% is advertising. So part of it is not e-commerce, but actually most of it. Okay, same goes for all of the other ones. So e-commerce is one of the largest industries nowadays. Some KPIs, which are what we look for in each of these verticals. So for advertising and targeting, the most important parameter is the customer acquisition price, which is how much are we paying to get each particular customer. So you might be paying Amazon, Meta, $10,000 a month, and then you want to see how many customers you gain from them. That's the most important parameter that they are judged for. Now, for e-commerce side is the conversion. So once a customer has arrived at the site, whether coming directly or currently, sometimes called, or through any kind of advertising, how many of those can you get to do a particular task? Say buy something, register, create a profile, that's also a particular property. So average numbers vary between 1% to 10%, depending on the industry, depending on the site. Okay, and I would say that the important thing to understand right now is while this domain is mainly based on machine learning and model companies, when you move here, so probably many of you have heard about Amazon, there are a lot of traditional multi-video retailers that when you speak of them as we did last year, you see that they have very nice websites. But those companies, and I will not mention names, but they are very respectable retailers. The DNA of the company is not of a technological company. It's a DNA of a retailer. So what does a retailer have? He has hundreds to thousands of sites. So he has to handle the stores. He has workers that do not look like of the same profile of CVPR visitors or ML researchers. Have the workers actually have to work in the store. So it's a very different organization. You will rarely find that they have any kind of machine capabilities. And I'm saying again, it's a different organizational DNA. Therefore, it's very difficult for them to go through a digital transformation. That's really where there is a significant lack of machine learning in the market. In particular, for the SMBs, the small ones. They don't have the funds, the resources to establish a machine learning tool. They just don't have it. You have to be very big in order to pay for machine learning researchers or other tools. So this was working very well until about a year ago. Everyone was very happy, we were making a lot of money, and then things happened. So chronologically, about 2 years ago, 2.5 years ago, Apple came up with APT. So APT is a way, if you can understand my English, it's really great technology. So it's different technology. So what happened? So and this is not only about Apple, it's only about the state of California that before that came with new privacy regulation. Europe is big on privacy regulation. So what happened with Apple? iPhone users are typically considered to be the prime customers. Those are the people you want to sell to. Therefore, they are very important for e-commerce sites. That's why it made so much influence. So the way to target them is to be very, very simple. There still is the IDFA for each iPhone, some 12 iPhones. It's a unique identifier per handset. So the thing about this, it's only identifies your handset. This allows, like a cookie, it allows interaction between different applications. So if you search for information about the audience about 2 weeks ago and say Expedia, then that event would have been recorded under your IDFA and then translated to some aggregate. The aggregate that sells the event. So Facebook might come up, buy the event, and then show you some advertisement about the audience. It used to work very well, amazingly well. As you understand, it's actually simple, but it's really a lot of technology. There are unicorns who work on that aggregate these kind of events. It's a huge industry of a relation of events. It's not that simple for us, machine learning people, we might look down at that, but it's not. It's more about the computer infrastructure. So maybe some of you have already seen this. So when ADT came along, you got this message for any application, it basically asks you, are you willing to opt out, to prevent, to preserve your privacy? So the way it was written and suggested, 75% of users chose to opt. This implies that suddenly Meta and the other Twitter and the other advertising agencies somehow, quote unquote, became like they couldn't see the evidence. It became much more difficult for them. Now, going back to the CNBC part, one part of our talk, look at the stock. Okay, look at the other companies that are similar to that one. That's part of the reason. Okay, also fingerprinting is not allowed. That's a technology that you probably know also for web browser. I can get a lot of attributes about you from your browser, from your handset, and then it is similar to what I'm going to discuss here. It's method learning. I can learn an identifier, like in face recognition, an identifier that will describe you. It's not allowed by policy. So if they catch you, Apple, they will throw away your app from the App Store. That's like that for an iPhone application. No one installs apps, not from the Apple App Store. So everything became more difficult, and this industry is actually changing. Yeah, again. Ehud, what did you do?
I have no idea, but it's worked.
Oh, that's the best solution, always. I recommend it.
Okay, try now.
Okay, thank you. So what happened? The customer acquisition cost in the last year surged by 200%. So it's less effective. This part is suffering. Oh, Meta, Snap, Twitter, Google, everyone is suffering. And beyond that, unfortunately, we have less of consumer spending in general, okay, because of the financial situation. So these companies are suffering the most. Okay, you can see that again, that's the safest part. Just look at what they are telling us about what's going on. And what I claim is that the convergence here can be improved for most of them because nowadays they're doing nothing. They got used to having a very easy going. They will go into some kind of web where they control the spending on the advertising companies. And if you wanted to get more customers, you will just pay them more. You will get more customers. It's very effective. Now it doesn't work. Actually, you're getting much less because the targeting is less effective nowadays. Okay, so I'll talk today about technology which works here within the e-commerce site, although it can be applied also here, but that's a different kind of industry. Okay, so what's multimodal text image embedding? You have two inputs, say an image and a text that corresponds for the content of the image. You embed both of them and start this embedding in detail later, and then we want to minimize some kind of distance. And you can either use a triplet loss, and recently a lot of works use the contrastive loss. It's also used in self-supervised learning. It's exactly the same problem in terms of network learning, and then you have to get a symmetric version of that because those losses are not symmetric. Okay, they're asymmetric. And that's and obviously we have how negative mining because that's network learning. That's what you do. So that's the very general thing that you're going to use. There have been a lot of works, just to say a few words, in particular because they're a challenge in this workshop. Challenges and data sets are very important. The first paper by Kappa, one of the first, probably there are a few more, many papers by Kappa and Faith, one of the latest contributions is that they proposed the splits in the Flickr 38K and the Coco data sets. Everyone is still using those splits. So it allows us to just compare and see the improvement. That was very, very important. I hope that the data set that was proposed in this workshop will also be used because those are becoming a little bit small. Okay, and so there will be a lot of architectural changes that I'll discuss later, but I think that the latest change came with Clip and now with Coca. Coca is by Google, it's from about a month ago, so these are foundation models. So the largest one which we know is have 80,000 images to train on, and then each image has 5 captions. So we get 400 pairs at most. Here, they train with 400 million pairs. That's 1,000 times more. And that's JFT. I think it's like 300 million or 500 million. It's a private data set, so I don't know exactly. Okay, but that's in the order of 1,000 more. And like in GPT-3 and this kind of huge models, you get this kind of zero shot properties, which are interesting, but from a practical perspective, are not typically very useful. But still, it's interesting to see what happens when you just increase the training set in such a way. So, just what are the tasks that we are judged on? The same as in the challenge in this workshop. You have image search, text wave, so you are given a word and you have to find the most similar images. So similarity is always measured in terms of the L to norm. Now, in practice, we like always use this norm because it can be accelerated. You can do approximate and to search. If you have 100 million images, or 100 million text, or 1 billion images, you can use hashing like LSH and other variations of that, and you go from linear search to log and log searches. So it should always be okay. Otherwise, it's useless. Okay? So, this is the right answer, and I'll come back to this image later because you'll see that there are some other conclusions here. The other way around is image annotation, image to text, so you get an image. So an image at the end of the day is just a vector. All of this text as vector, we just look for the closest ones. And just thinking for a second about the e-commerce, think about this, about the way to do order discovery. So you can go to a website, write what you want, and you'll find it. So despite that, in general, it doesn't work. I'll tell you the second why. But that's like the immediate application. Most websites nowadays, e-commerce site, they have this search. Okay, that's the regular way to approach them. Image annotation is rarely used. You can upload an image and then using this kind of technology, get that. It might be a text, might be attributes, you can do a lot of stuff with that. But it's rarely used. Okay? But these are the metrics that you are jumping on. The symmetric retrieval metrics. So what do we care? So why would we like to apply to e-commerce? And also this applies to what I discussed in this talk. There is a discrepancy between what we can capture and analyze from images and what we can capture from text. So with images, it's very obvious we can understand low-level visual cues. Sometimes it's color, texture, shape, whatever. All of us do that. But text, either being speech or being regular text, NLP-based analysis of that, has a property of encoding high-level semantic notions. Okay, so just to give you a particular example, look here. So you have a corresponding image and the text. So if you analyze the image, obviously, you can find the shape, you can find textures and so forth. But there are some high-level semantic notions that are given in the text, like business people, so where people, business, working. These high-level semantics and the word. So I think that most of the, if you just look at the image, you'll be able to find attributes, okay, to define them. But it could be much more difficult to train a method to do. And here it is given to you for free. That's a very simple NLP problem, just to take a sentence and then embed it. So that's difficult. You know, especially in the age of birth-based models for sentencing them. So the point is that there is a discrepancy between what we can encode with each of these different modalities. And again, Michael discussed that when he talked about 3D shapes, which we don't call 3D shape, but it's the same thing. It's one thing to look at a 3D shape and say that a person is high or low, whatever. But if it's just given to you, it's much easier than to utilize this information, and there is a lot of text. I mean, if you just think about e-commerce website that you can scrape, take all of the images and corresponding text, and you can think about all of the text that is in the internet. So it's easy to learn text. In particular, some of the best models are not still third model, GPT models, still for free. So that's the main difference. And text also allows you to encode attributes. So the word small and large has a different semantic notion generally than if you go into a fashion website. This, this is small, large, etc. So very different context. So you can use this kind of event not only to help embed the images, but also embed the attributes. So you always have the attributes on the left side typically. That's the common framework website. So you have image, you have text, and then there's some attributes written down. Because the e-commerce site, how does he get the data? He has an Excel file or XML file, whatever kind of thing, and there's attributes for each product itself. So we looked at that, and it's easier to understand why that's important. Also, most people, and I'll say it in the next slide, they don't look for a particular. They search semantic. No one looks for this search, for this shirt, but people do look for a short-sleeved shirt of a polo design or whatever. But this is semantic. This is nothing to do with the attributes of this particular shirt or your shirt. Okay, so search is typically semantic, and then you have to reduce the semantic notion into your representation. So this part will give you the semantic part, and the image that should give you the appearance. There are many other applications that I will not discuss today about medical imaging. Think about an MRI scan, and then the diagnosis given by the radiologist. So typically, the MRI scan and the algorithms that are used for that, they capture low-level image appearance attributes, but then the physician, the radiologist, doesn't discuss it. It gives you a full diagnosis. Okay, what does he see in general? Is it a healthy person, a sick person? What kind of phenomena does he see in the image? Medical one. Same also if you want to detect hate speech, fake news. This combination of text and image is very powerful. So after trying to convince you that it is important, so what did we do? First, we identified that there is a problem with the way this problem is set up. The main problem is that also in this workshop, you're only given identical pairs. All other pairs are given as negative. Now in practice, and I'm showing this image again, so you take the vector, which equals this sentence. So this is the right match. This is the identical one. But this is also seems to be identical. This also, so in practice, there is a third category. There is positive, negative, and similar. And similarity is very important because, as I've told you, there are two main ways to think about it. The first one, from a data point of view, our data is actually part of a manifold. The notion of a manifold implies that for each point, there is a set of points around it. There are no isolated points. And this is the property of the data, not of the algorithm. So if you're considering a particular data set that comes from a particular application, then typically, because the entire data set is in some sense low dimension because it's all about fashion, then you would have a manifold structure. So there will be similar pairs. And the way we set up the problem is not only about us, it's about everyone. The way the algorithm works is that all pairs that are not identical are considered negative. And when you do the hard negative binding, that's the way we got it a few years back, you keep getting the similar ones as negative. It doesn't make sense. I mean, because they look very similar. I mean, one could actually, if you don't know the right answer, you could just switch them and it would be the same. So what we're trying to do is to reduce semantic similarity, to reduce the manifold structure. I'll show you in a minute. Going back to e-commerce, no one, the average query in e-commerce is about 2.8 minutes. That's it. That's what people write. No one goes in and writes 5 sentences about my shirt. No one. If you just if you just count it, it's about 3 words. So no one actually has a particular aim. It's very broad. So those KPIs, R1, the accuracy measurement in R5 are only used for training the network. In practice, there are many things. And in practice, what you really want to find, or you want your product or your network to return, are the similar items. Because the user never wanted this particular one. Never. Maybe that's the closest one. But that's not what you wanted, because just use 3 words. You probably have to be a fashion professional to be able to describe this shirt exactly. I don't know how to do it, maybe some of you know, but it's difficult. Just think about it. To get this product, and if you go to a large website that might have thousands of shirts, how would you describe this shirt? Difficult. And no one will do it because you just are going to spend up to 3 words. So it will be difficult. And actually, the way to do it is to understand that this is a kind of multi-model. It's like ImageNet in the sense, model in the sense that it allows you to encode the data. That's not the purpose of what we are trying to do. We're going to define a downstream task. So there is no multi-model embedding just to retrieve data, because first, it doesn't work. Second, we don't really care about it. We just want to get a full joint embedding. And what we found is that then you start encoding what is called the user journey. So any site has a user journey. You go to the site and you start doing some actions until you find the item that you actually interested in. So that's called the user journey, this set of actions. So we can encode the set of actions and then start trying to optimize it to do various tasks and predict the next step, just to shorten the time. There is a significant correlation to the time it takes to find the product and the probability of actually finding it, so you want actually to reduce that, and many other tasks. But the bottom line is that these type of models are actually like foundation models. You just want to embed the data. So what did we do specifically in this paper? In order to induce similarity, we took a variation of Mankur's paper about the center law. So it's not a paper of center laws, it's a variation of that paper. That's a paper about instance segmentation. So what's the idea? The idea is that you quantize your data into centers, into clusters, and implying that you have centers that you compute the centers, and then you induce a loss that forces samples to be close to their centers. And there is another term which causes the centers just to become a distance. So you will not get significant overlap. Now, and the focal point is that if you just, so in order to initiate the process, if you just do nothing, do the regular embedding, you get this thing. So you already have this kind of manifold structure. So we have a good starting point. And what we wanted to do is to utilize that to further improve the manifold structure, to create this third class, which is similar items. So that's the loss. And the interesting thing to say that since this is dual embedded, so images and text are being embedded into the same space, there is only one set of centers in the dual embedding space. Okay? We don't need centers for images and text separately, the same set of centers. Okay? So this implies that a certain set, that for a certain center, all of the samples belonging to it are actually considered the same. Okay? And we use soft assignments to make it smoother. So optimization would be easier. You can also use hard assignments, so each sample belongs to a particular center, but it's nicer than the view of like thing showing a second is well known. So what do we do? We train once regular embedding like before, same thing. Then we quantize the data and we initiate the process we continue training by adding the additional laws I just showed. So this is the original embedding network. You can use whatever embedding you have. More advanced because that paper was done like 2 years ago, 2.5 years ago. Whatever you do here, just to do the original embedding, get a little bit, it does do the same. Once you have that and quantize your space into a set of semantic notions, you add the center loss and you pre-train this MLP, which computes the association with those numbers that I just showed you. Okay, so everything is now being trained all the time, so end to end. And just to show you the results, so these are different backbone networks. So those are the first, the BGD19 and version 152, and we get a significant increase. What we're seeing here are annotation. Annotation is image to text, search is text to image. This number is just the sum of the 6 numbers to the left. Okay, it's the easy way just to look at the overall image. Okay, and once we have a more advanced embedding algorithm, it's not ours, just another text image embedding of using these papers, we still have some improvement. Okay, but also one thing that you should remember that the deeper the network, the better the result, regardless of how. Okay, regardless. If you have deeper networks with more parameters, it works better in this domain. And for Coco, which is the largest one, you get the same kind of. Yeah. So then we started working on the next paper, which was 5 minutes, 7 minutes. Yeah, no questions. No. Okay. So what did we do? So just to tell you again, the image is being analyzed by an object detector, and you get a set of ROIs which should be there. Typically 36, that's like a magic number. Now we have to pull them and encode them by a single vector. Same goes for the NLP part. So what happened last year? There was an oral paper last year by Chen and Associates. So what they did, which was to replace the text encoding by BERT. We couldn't do it because we couldn't then compare to previous results. The previous results with the GRU and the planning layer, but that's the next thing. And they have their own pooling method. And we concentrated on the way to put the visual features. That's what I will discuss next. And for instance, for Coca, published last month on Archive by Google, they use a very simple pooling mechanism based on a conformal encoder. So remember, each image has 36 vectors, which are the detections. You just put them into the conformal encoder, and you have a CLS, and then you just use the CLS as the pooling. If you read the paper that introduced BERT, you get this exactly this kind of pooling and other mechanisms for that. So this is what they did. They only use the detector of the computer. So working on fashion data, we started using additional cues. So if you want to pull together all of the detection, you really want to use additional cues, not only the appearance, you also want to use the location, the size, the color, the detection. So you have many cues that you can use. The way to reduce the input conformal encoder is through special event. Okay, so we tried all of the many ablations through positional encoding. Positional encoding allows you to change the interaction between the vectors. So if you just have the parent vector, all you get are the inner products between the parent vectors. So positional encoding allows you to add something else that changes this inner product. So what we wanted to do is add all of these attributes, and after operation, we do that. It's enough just to use 4 of them, which is the location and size of the object. So we just quantize them and then add them as positioning coordinates. Basically, it implies that if you have an object here on my left-hand side, and an object on my right-hand side here, they will not interact. Different objects. And there is a lot of information because my head is about my shirt, is about my pants. So there is an interaction that can be learned, and the consumer encoder is going to learn all of that. Another issue, we didn't introduce color yet, but remember the detectors typically do not encode color. So if in your detector there is one class for shirts, so my shirt and your shirt are the same class. And since we have different colors, then the detector knows to be variant color. So color information, which is very important in fashion, is not encoded here because we use a detector, prepaid one. Okay? So once we do that and we use max pooling, we get significantly improved results over the results from last year. So when we compare on the figure 30K, we get an overall improvement of 20%. So that's 20% overall different KPIs. And here for the COCO 1K, we get an additional improvement. And I think that the bottom line is that it's like cooking something. The more information you put in, which is informative, the better it is. So this is basically what we did here. We just cook. Okay, then all of this previous works just use the appearance vector, which is rather limited here. And we use additional information. You may think about this thing as having some kind of signal encoded in our representation. That's basically what we're doing. So, conclusions. Embedding the semantic similarity as part of your representation improves the performance for any vector. Then if you use more cues, there are many cues in practice that we don't think about it in the academic regime, but existing in real application. Let's remember that the detector-based appearance vectors are very limited. Larger models improve performance, so it's better to use BERT than embedding in GRU, that's obvious. It's better to fine-tune your BERT on a particular domain, not just use the vanilla BERT. Okay, you can use examples, those were used by Chen and Associates, they also improve larger data sets. You can do all of that in a real application. For e-commerce, so multi-level embedding is actually essential and very informative. You can add additional outputs. Again. So for the last slide, so how to survive when you try to actually use it in a real application. So what is the Kobayashi Maru challenge? So anyone knows? Yeah, Star Trek. Yeah. So it's a recurring thing from Star Trek. Comes from first appears in the Wrath of Khan, the second movie. So what's the story? I have 1 minute, okay? I have 1 minute. Yeah, it's the most. So there is this challenging space academy that any cadet is destined to fail. So you cannot win. Only one cadet ever survived it, Captain Kirk. So what did he do? He hacked the system the day before, and then was able to survive it and win. So what's the bottom line? So 2 things. First of all, cyber threats are always come from the inside. That's the first thing, even in the future. But the real bottom line is that you have to think differently when you're trying to apply this kind of algorithms to a real application. Okay? Because in a real application, you can change whatever you want. You can change the way the application operates, you can use more data. The rules that we are using, say, in this workshop, it's a challenge, and everyone has to obey to them, or just because we have to compare. But if you have a real application, you can just do whatever you want to improve performance. Okay? So, thank you. I'll be happy to answer questions. We have time for questions?
Yeah, maybe we can have a few.
Yeah, thank you.
Maybe also from online, if there is anyone. Okay, so I'll ask. Oh, go ahead.
I have a bunch of.
Go ahead.
Yeah.
Yeah. Basically coming from one of the biggest e-commerce services we can usually we are 4,300 we make over $50 million a year, and we work daily on multi-modal data embeddings and goals data people to enhance across the board tasks. One of them search engine in search. We look at a bunch of applications. The first question goes back to the logic of text to image embedding. We look at having a multi-branch model that look at the image, the text, like find and overlap in manifold space, maybe to embed code. Sometimes we have very complex products. Think about valves. A valve. You know what the valve is?
Yeah.
A valve would be the you find a product like it's called a valve, diameter 20 inch, length 14, for example, 1 feet or whatsoever. And those products are so technical. It have lots of dimension involved in it. There is no beauty like a person is sitting or like a bunch of people are wearing like a shirt or whatsoever. Have you ever had any experience with embedded image and text, like multimodal embedded in the case of industrial products?
We mainly worked on fashion and furniture on the e-commerce side. I think that when you move to products where actually the semantic issue is not that significant, you can actually use the regular system. Typically then you can build a tree of attributes and then just choose them. So to go to the extreme, if I want to buy an iPhone 13, you don't need multi, you just need like textual matching. Okay, so if you have very clear attributes, and it's not really semantic. It's not like I want a shirt for CVPR meeting and with short lips. That's a semantic query. So if your query is very particular, I think it actually goes to the NLP side of the problem because you don't need the image. Yeah, you just need to be able to do that. So the question then would be, do we just identify this kind of keywords, or can we use embedding in the text domain? I think that this goes more to the text domain and not to the multimodal because the image does not contribute much.
That's true to some extent. Sometimes the image is stronger than the text, especially when it comes to like electrical plugs and relays. Images are stronger. Second thing is there's a lot of semantic in the sense where the text is a proxy, can be proxy to the functional use of the product that involves lots of expertise and technicality. In the meantime, we are looking at the cross and upsell. Semantic has to be there to find dependent products. My last question, it's a very interesting topic.
I'm sorry, but we're going to have to continue. So we're going to have a break now for 25 minutes. We'll continue at 20 past 10.
So we'll take it offline.
Yeah, so you have time now to take it offline.
Appreciate that. Thank you very much.
Thank you. כן, בוא נשמע משהו. רגע, תן לי שנייה לשאול.
Is it like contrasting laws?
שזה ככה, אל תגמר. שלחת לי את זה בוואטסאפ. אני יכול לשלוח את זה, שאני אשלח את זה במקום אחר. זה מחשב של שירן, הוא לא סטאפ כזה עד הסוף.
The schedule for this morning so workshop here.
Sure, it's in the website, but also right here.
Okay, thank you.
אני רוצה להעתיק את זה משהו. Sure. By the way, can you access Google Drive when you're in the United States?
From where?
Oh, usually from here. Because I was worried that it's not going to be accessible from everywhere. Google Drive.
Where should I go first?
Should you go?
You want to find a Google Drive of this thought, or?
No, it's okay. It's okay. Thank you.
We keep Kayam.
No, you can.
Elimination.
שלחת לי לינק לזה.
חשבתי שאני אבוא לחבר מחשב ואציג, כאילו, עברתי עם הכל מוכן.
Yeah, unfortunately, because they want to be everything to be recorded and via Zoom and so on, so it's better to have everything at the same computer.
I was under the mistaken assumption that they would actually have a teleconferencing system in place where the output from the PC would be recorded, and I could just switch in the PC,
Yeah.
and not just a Zoom meeting that somebody opened up.
Yeah, at first they said no to any kind of recording because they thought it's going to be too complicated, but I guess they said it for this one.
The question is, will the embedded fonts embed?
So Rocco, what is I didn't really understand the connection with you and Marina because you work for Grotini Lab, but also part of the university. Or
Yes, I'm a collaborator with the research group, external collaborator, and now I'm about to join them again. So
wow.
I will be with them in a few weeks.
Like in what kind of way? For a
As
short while?
researcher. No, as a researcher at the university. I applied for a position and I'm under examination.
So you will be living at Grotini Lab?
Yes, but Grotini Labs works together with the university with so many projects, so it's something like big family. So I will not leave them in a strict sense, but I will still work in retail, but on the side of the university.
So do you
also teach all the other activities.
Are you in the same city?
Not, but they are 20 minutes by car. So
Okay, yes, close enough.
close enough.
Cool.
I got my PhD together with Marina, so I know.
So you decided that you prefer to be a researcher instead of more like a product oriented person?
I don't know. I have this opportunity, so I decided to get it because it doesn't happen every day. So
Cool. Good luck. Yeah, it's very interesting because from what I saw, the Routine Lab is working many things that are like very, very similar to what Praxis does,
Yeah,
as well as many other companies.
much smaller, but we try to.
How big is the company?
It's 15 people, so it's a very small company.
So this is the fun side.
Yeah.
How long does the company exist?
10 years, maybe 15. No, I think no more than 10 years.
Ah.
So it's really young.
10 years.
Yeah.
So you say 10 years is young.
Yeah, 10 years.
Always, it's a long time. Yeah. But compared to the big company, of course, it's very different.
Am I going to have a presenter view when this comes up?
Yes, I think so. Yeah, so I hope the recording will be okay, but we'll have to see tomorrow.
I assume you don't have any speaker video, or do you?
No, it's this camera.
So actually, I might stay here and then
Yeah.
have video. But
Yeah, but if you don't remove the mask, then,
no, I'll take off the mask for the talk.
or we should have very expressive eyes.
I've gotten pretty good with that. 2 years practice.
Nice. Let's see what we have next.
So, what's your seat affiliation?
He's a professor at Bar-Ilan University.
I said completely because he started about concept preposition and then went into embeddings and text. I missed the connection. What?
Nice. Okay, hold on.
Oh, that's not good.
Let's see.
Oh, open read only. Maybe I can actually. Oh no, that's terrible. I'll send you the font. No, everything's terrible. I need to fix that. I'll send you the
Okay.
font.
Okay, go ahead. איך קראו למצגת שלך? זה זה? כן.
Yeah.
כן, יש שזה מקליט.
Can you open my presentation again so I can see the fonts that it's complaining about? Close it and reopen it. It pops up a message. Can you open up your email?
שלך?
No, you
מה אתה רוצה לעשות? יש מצב שזה...
אל תגלה לאף אחד שזה בכוון. אני דורש רישיון.
בסדר, אחרי זה שלח לי איפה יכול כתב.
צריך לסגור את הפאורפוינט לגמרי, אני יכול לסגור? בטוח אני יכול לסגור.
זה מול הקשר להם.
הוא על הפתיחה. אנחנו נחזור?
אז זה מה שאני אעשה. אני צריך קשר...
שמנו שזה פונט מסתתר פה שלא הצלחתי להעיף שם.
בסדר?
אבל אין לי פרזנטוריה.
טוב. כדאי קודם לקח לו כמה שניות.
הכל.
תגיד
אתה
לכם,
רוצה לבדוק רגע שזה משותף לדבר נכון? שנייה, נסתכל בזום. שהוא משתף למסך נכון.
איך אני מתקשר לספרת הלבית?
1 פלוס, כאילו פלוס 1, ואז המספר. Cool, okay, should be fine.
אתה יכול לתת מזה?
סבבה. קולי, הצלח.
כן, נראה. נראה כמה מספר אמריקאי? אני אעשה קשר למספר הזה.
We can have a.
Yeah, sure. Happy to talk later. Send me an email or.
Yeah, I will.
No, LinkedIn email is okay. I'm free after the workshop.
Maybe I can. After this is when season. Yeah, maybe we can.
I think it's just like a sandwich. Okay, but I think it is lunch. Yeah. Not at lunch. Let's say 1 o'clock.
So I wonder where that feeds.
No, it was here. You need connector for HDMI.
Yeah, we were just gonna.
Yeah. אחת הדוברות עדיין אולי לא איתנו, אבל נראה בהמשך. Okay, so now we'll have the talk by Alibaba that will summarize the challenge that we had. It's going to be 10 minutes, and then we continue. There will be no Zoom questions after this one.
Hello, everyone. This is Ken from Alibaba. I will give a brief introduction on Ali Products 2 challenge associated with the RetailVision workshop and CDPR 2022. I will talk about the new version of the Ali Products dataset and then announce the winner teams of the challenge. This year is the third year of the Ali Products challenge, and it is a multimodal upgraded version of our previous image-only Ali Products challenge, which had more than 1,000 teams participate. This year, the challenge is based on the Ali Products 2 dataset that is designed to bridge the gap between visual representation and high This realistic large-scale and multimodal dataset consists of 4.3 million image caption pairs of 100,000 fine-grid products. Challenge participants are expected to find the top 8 product candidates to match a given query, such as blue men's turtleneck sweater. In real-world applications, to develop a large-scale cross-modal product retrieval model, we may face a lot of challenges. For example, we may not be able to obtain a large number of product image text training pairs with text information such as titles. And the training data may be unbalanced, where some unusual products, text image data is insufficient. Additionally, in the training data, the text title is not always completely related to the image content, which makes the text titles noisy. The dataset is accessible after the registration for the challenge. The format of the files is listed here. The training set is not annotated by human, and some classes can be quite noisy, while the validation set and the text set are fully annotated. This year, a total of 674 teams were signed up for Ali Products 2 competition. And during the final testing phase, there were 27 teams who submit their results. The leaderboard is listed on the Tenshu Computation website. The winners go to the team with the highest mean score of report 10 and report 5. The first place goes to 大我带带我 team from Meituan, and the second place goes to team Zebra AI team from Zebra Technologies, and the third place goes to Needham Bicycle team from Ant Group. Congratulations to the winner teams, and the technical reports of the winner teams are available on the website of the RetailVision workshop. Many thanks to the organizers and the participants of the Ali Products 2 Challenge associated with the RetailVision workshop and CVPR 2022. We hope to see you next year. Thanks.
So thank you, Desi, for this talk. Just take a minute to set next talk, and then we can continue. Oh, right, a different user. It will be best to show to this email instead.
I would just give you access.
Yeah, just a different email. Okay. So now we have Ning Zhang from Meta AI, still used to the old name. Okay, so we have a clicker over here. And
Hello, everyone. My name is Ning. I'm from Meta AI. So Meta is the parent company of Facebook, if you don't happen to know that. Today, my talk is about the future of AI-powered shopping. So what we believe is the future of commerce will be powered by AI, and we will provide bespoke shopping experience to create meaningful connection to the brands we love. So we also believe that we want to leverage AI to strengthen our understanding of the people and the brand, and connect people to the products they love. So ultimately, AI will drive experience across the commerce funnel, from discovery, consideration, reconsideration, checkout, and re-engagement. So from like sellers, merchants, they want to onboard their products, to people who want to find the product they love and to reconsider the product they're looking for, the whole funnel will be powered by AI. Our team focuses on AI-powered commerce for Meta, and we have strategy for two things. The first thing is making everything shoppable, meaning in the future, we want to make sure every video, every image, every conversation, and everything you see around in the real world, in the metaverse is shoppable. And other strategy is making shopping personal. So to connect you from the brands you love to the styles that suit you, your budget, your body, etc. Want to understand user 360-degree. So today, in this workshop, of course, I'm going to talk about some technologies, some AI technologies we do. So what is under the hood of all the work we do? I will mainly focusing on multimodal representation learning. I think people are not probably are familiar with what multimodal understanding is. So given all the billions of product merchants uploaded to Meta, to Facebook, Instagram, there's a lot of modality, different information. Like you see, this is a typical catalog, what you want to shop. So there is an image, there's price, there's brand, there's information about this dress. So we want to help shopper find the right product by understanding the category, like this is women's dress, and also understand the attributes. Like this is a black bell sleeve dress. So we can help shopper to find the product they like. And then we do this by using multimodal understanding to use the image here and also the language and other modality, metadata associated with it to help to do this category and attribute prediction. And then the model we are using it, not surprising, we're using a multimodal transformer to do this task. So as you can see on the left side, there's the input with the product image and the product title or some user's caption. We have two encoder, the image encoder and the text encoder. The image encoder is some other pre-trained image neural network to extract features from this image. And then we feed this text token, this description is tokens into the multimodal transformer. We feed the image feature in its tokens, and after multiple layers of multimodal transformer, we use the class token to predict the category and then the attribute. So how is this useful? Think about it, this image, we identify these attributes and the category of the product. We can show user similar white t-shirt, is this white t-shirt, and similar denim overalls, or similar plotted pen, plotted plant pot here. So to help the shoppers to find the right product. And there are so many different attributes and different categories. And if you consider, if we have like 1,000 categories and 1,000 attributes, then we will have like 1 million different combinations of a category and attribute. So in order to do a supervised task, it requires a lot of the training data to do so, which is not scalable. So in this paper, we consider the compositional object and attribute classifier to learn first the object and then the attribute, and then using a 2-layer MLP to associate the category and attribute, this can generalize well to some unseen attribute in the category combinations. Like here, the example show the compositional attribute could be geometric pattern, kitchen island, which hasn't been shown in the training data. And the next, I'm gonna introduce our latest work called Commerce MM, Large Scale Commerce Multimodal Representation Learning. This is a paper to be represented in KDD this year. So when we think about using large scale unlabeled multimodal data, which is usually a large, noisy, computationally inexpensive data we have, these images and text in our platform, what we do is we want to do two stages of learning. The first stage is what we call pre-training. There are a lot of latest work in multimodal pre-training. And after pre-training, we use the same model to fine-tune on the downstream task. Usually the downstream task has small, clean, and labeled data. I will show you in a minute what a pre-training and downstream are. So our Commerce MM model aims to use this commerce multimodal data, and we proposed different pre-training tasks. We have 5 image and text-based pre-training tasks, and the 9 we call omni-retrieval pre-training task. After these pre-training, for downstream tasks, we have these different downstream tasks. We have catalog categorization. We already seen some example of this. We have image to text retrieval, text to image retrieval. This is from image to text. How do we do cross-modality retrieval? We have query to product retrieval. This is to help with text search. So you have text query. How do we find the best product? And then we have image to product retrieval. This is aimed to do visual search. So once you have product image, how do you find on Instagram, how do you find the product associated with it? And then we also have image to image retrieval. Once you see a style you love on Instagram, how do you find other style similar looking to that? So let's talk about the data we have. So if you think about multimodal, what we focus in this work is mostly image to text. But just beyond what you see on the right side, the product page, which contains this product image and title and description of this short sleeve dress, we also have some other association with it. We know what user searched, so we can associate the search query with the product page. We know sometimes user tag a post. So this user was wearing this dress and tag this dress in their post. So we know this multimodal to multimodal association. We also have image to multimodal association. Is this image to the product or image tagged by the user to this product? So we have all sorts of this association we want to make use in our pre-training process. So in the end, we collect over 150 million data. It contains about 50 million data of these product posts you see, and the 52 million of the marketplace posts. Marketplace is also what our another shopping platform, Facebook has. And then we also has 50 million of cross-model, cross-peer data, which is the shop text search query with the click product and the IG and Facebook post where your product tag on the post. So these are noisy data. Doesn't necessarily mean this text query is this product, but user click it. In terms of model architecture, similar to the transformer model I showed in the beginning of the slides, here we have this image. We use grade level feature, similar to the vision encoder can be ResNet or VIT. If it's ResNet, it's a convolutional feature. If it's VIT, we separate the image into grid, and each grid is encoded into a feature token. And the text, and we also have a text encoder, is also transformer based. And then after image vision encoder and text encoder, we concatenate the class token feature to all the tokens feature into the multimodal fusion model. And then the multimodal fusion model is gonna produce this vision class token and the text class token. It's also a transformer based. We did some clever trick in the paper to be flexible in terms of the text encoder, number of layers in the text encoder, number of layers in the multimodal fusion encoder. This is to give us some flexibility in terms of different latency requirement. So in terms of the pre-training, we have different pre-training tasks. The first is people are very familiar with mask language modeling. So we are mask 15% of the tokens in the text encoder and ask the model to do self-supervised learning to recover the mask tokens. So if you look at the loss function here, it's very clear. We want to just mask some of the language and then recover this language in the end. And after the language, masked language feature, we also want to do some masked image modeling. We have two ways of doing masked image modeling. The idea is similar to masked autoencoder, that you want to mask some part of the image and ask the network to be able to recover it. The first thing we do is in feature regression. So instead of recover the image in the pixel space, we want to recover the image in the feature space. So given this original image, we mask about 50% of this image and we produce an embedding. This embedding can come from some pre-trained network on images. So we have an internal image encoder on images only. So we produce this image embedding. And on the original image, we also have a image embedding. So the network is to learn to regress these two image embedding to be similar to each other. So you can see in the end, we are doing feature regression to minimize these two features. And the second feature regression we are doing for mass image modeling is around KL divergence. So this is, instead of doing a regression on the dense space, we cluster this dense space into clusters and we regress to the cluster IDs. So for these clusters, we have a predicted probability of these features falling into each cluster. And then we mask out image and then we wanted the network to reproduce this cluster ID. So this is a second mask image modeling. As you see, the objective is to minimize the KL divergence. Other things, pre-training task and text contrastive learning. So remember, we have an image encoder and a text encoder from these two class tokens. We want to be able to learn the similarity between text and image. So this is very similar to all these contrastive learning laws that we want to learn the positive pair, they are similar, and for the negative, when they are not similar, they should have a larger loss. So this is on the image and text contrastive learning. And then the last of the common image and text pre-training laws is the image and text matching laws, which we feed the whole network of image and text encoder, then multimodal fusion encoder. And in the end, we have positive pairs that is going to be positive, and negative pairs is going to be negative. So this is the image and text matching laws. So as I said, these are the 5 image and text pre-training tasks that is commonly used in the image and vision language pre-training, mask language modeling, mask image modeling, and image text contrastive laws. So as I mentioned earlier, other than the normal image and text association, we also have these association from different modality. We have text to multimodal, multimodal to multimodal, image to multimodal. So we formulate this problem is cross-modal, cross-modal, cross-pair data. So we have a source pair is image 1, text 1, and target pair image 2 and text 2. Just to note here that not all the modality is available. Like sometimes we only have text 1 to image 2 and text 2. Sometimes we only have image 1 to image 2 and text 2. So our assumption here is if a source pair is linked with a target pair, we assume any existing modality from the source will be highly correlated with any existing modality from the target. So what does this mean? So in this illustration, for just the two pairs, source and target, we can always produce three embeddings: the image encoder embedding, the text code encoder embedding, and the multimodal embedding. And we have these 3 by 3, 9 different associations to associate these two pairs. So there are 9 cross-modality combinations can result in 9 similarity matrices with each batch. So we use this 9 different similarity as an additional 9 cross-contrastive loss in our pre-training task. So after we pre-train the model using this 150 million data, now we go to the second stage of this model is to work on downstream tasks. As I mentioned earlier, our downstream task mainly consists of categorization tasks, which is given this image in the description to predict the category and attributes, and other omni retrieval tasks, so doing image to text retrieval, text to image retrieval, query product retrieval, image to product retrieval, image to image retrieval. So these are the main downstream tasks we run our model to evaluate the performance. The way we do it is for categorization, we use the class token out of the multimodal fusion. And for cross-modality retrieval, we either use the class token come from image encoder or come from text encoder or come from multimodal encoder. Depends on what kind of retrieval it is. So let's look at some of the results. So we compare with different pre-training tasks we introduced in this work. And we report on different tasks. So there's CC, MPC, T2I, I2T. So CC is categorization catalog, and PC is categorization marketplace. And then the other you can guess is text to image, image to text, query to product, image to product. And then we report this meta average, which is the average of 7 task results. And the first row is without any of the pre-training, just fine-tuning on the downstream task. And the second row is using mass language modeling. And as we can see, the language pre-training is better than no pre-training. And if we look at other pre-training tasks, where we have mass image modeling and the mass language modeling, what we see is mass image modeling is more effective than mass language modeling for the commerce tasks. Once we add more training pre-training tasks, the performance is going up. So it shows each of these pre-training tasks is very effective. And in the end, we try this omni retrieval task. It's also very effective, especially on the cross-modal retrieval of Q2P, I2P, and I2I. And in the end, when we have all the full combination of all the pre-training tasks, we get the best pre-training results on all these downstream tasks. We also try to transfer this to academic data set using Fashion Gen. It shows our small pre-training model, fine-tuned on Fashion Gen, we can achieve better performance than some of the existing work. So here is the most of our detailed technology. Now I want to show you where are these research being applied in our product and where can you see our tech. First thing is AI assistant tagging. This is to help sellers sell more. And this is contribute a percentage of our GMV. What it does is we sellers want to tag product on their post, and then we use AI to suggest tags to sellers when they post content that contains product. And we launched Instagram product tagging feature. Everyone can go to Instagram to tag product. So what it does is it use image to product retrieval, right? Given this image, we want to find what product is in it. to do visual search to suggested tags for sellers. So this is one place you can see our tag. We also have visual search available on post and the live camera. On Instagram, you can see it on live camera. You take a picture of this person wearing this outfit, and you can search the t-shirt that they're wearing and the pants they're wearing. On Facebook is available for business posts in feed. And as I said earlier, we want to make everything shoppable. This include the image and video, and also include conversations on Facebook groups. There are a lot of people discuss products. People will say, I'm looking, I have oil skin, what sunscreen do you recommend? Well, it is very important in New Orleans to have good sunscreen. And the people will say, I have oil skin too. I really like this Shiseido City Block SPF 50 sunscreen. And then we detect this product name and the product brand from users' conversation, and we find the most similar product to suggest to them to buy. So this can introduce new ways people can discover products, shop more confidently through our communities. So I think these all I want to discuss today, and all this great work will not be possible for all the team members in the booth. I want to thank them, and I can take questions now.
Okay, so I would like to ask something.
Yes.
So you're talking about, so first I like it, you talked about the captions being long and not the same as what the user search for. And it seems that you actually do treat them both differently. But you said that the information is noisy. So when the user searches for something, you see what it clicks on. And obviously the best thing to do would be to know what exactly the user would have wanted, and then to compare against that. Do you have any thoughts about like how much are we losing by not having the perfect ground truth and instead looking at what was clicked on?
Yeah, so in order to look at like what people click on, definitely is noisy, right? It also has this like feedback loop. If your search engine start to be very bad, then people click, probably you're not good either. I think when we deal with this in the training stage, we mostly use these weekly supervised data, these noisy data. But in the evaluation stage, we have like human annotated data about what people like give them a list of product, they rank on what they want the most, what they want the least, and we use that to evaluate the models that we have. But definitely you cannot know from billions of products what is exactly product they like. But this already handles some problem of feedback loop and proper evaluation using human in the loop.
Any more questions?
What is the order of the data sets that to be used?
So I mentioned in the pre-training is around 150 million. In these downstream tasks is in the order of 10 million. Yeah, it's in a round robin way, so sequentially. Yeah, we also have this secret I didn't mention in the talk is how do you combine different loss function. So right now is a hyperparameter, like is different weight, like different coefficient to control different pre-training tasks, and it also matters too.
Okay, so if this is it for the question, so thank you, Ning. And we'll continue at 11, just so we'll be exactly with the schedule. So we have like an 8 minutes break.
Thank you, Era.
Thank you.
Yeah, so like sending the line, get the batch, and then they say, the batch. Yeah, okay.
Okay, so thank you for sticking around. Let's continue. So now we have the talk by Marina Paulanti. The talk will be pre-recorded, but then she will be with us later for questions via Zoom.
Good morning, everybody. I'm Marina Paulanti, assistant professor at the University of Macerata and speaking market region in central Italy. I would like to thank Ed and all the organizers for this invitation, and I'm very sorry not to be with you, but unfortunately COVID prevented me from doing so. I belong to a research group called RISE, which stands for Visual Robotics and Artificial Intelligence. This group consists of about 30 people, including professors, postdocs, and PhD students that span 3 different universities: Università Politecnica delle Marche in Ancona, which is the RISE headquarters, University of Macerata, and Sant'Anna in Pisa, which are much for the biomedical application of artificial intelligence. We come from the experience that we have done in the last 10 years together with a lot of worldwide companies and some Italian companies that work with us in this kind of domain. These 10 years of experience enable us to assess consumer behavior from different aspects. I will tell our experience about human behavior analysis in retail environment until to where we are today with the analysis of human trajectories for new store simulation. In retail environments, understanding how shoppers move about store spaces and interact with products is very important. While the retail environment has several favorable characteristics that support computer vision, such as reasonable lighting, the large number and diversity of products sold, as well as the potential ambiguity of shoppers' movement, mean that accurately measuring shopper behavior is still challenging. After moving into the era of negative data, machine learning approaches evolved into deep learning approaches, which are more powerful and action-free and deal with the complexity of human behavior. The combination of high-resolution data and video information has led to new challenges opportunities for activity recognition and people tracking for many retail applications based on local environment interaction. The idea is this. The idea is that we want to measure and understand 2 levels inside the store. We are in the store, we are in front of a shelf, and we want to measure what people do in front of a shelf. How people grab the shelf, how people select and select items on the shelf, and then how do they move across the area. This is done using multiple cameras and understanding how the people move across the store using multiple cameras you more later on. Our research is performed with test installation installed in Europe, China, and also in the United States. I will present results based on 2-year experience that measure millions of shoppers and millions of interactions. For each purpose, a public dataset is collected and shared together with the source code to ensure comparison with the proposed methods and future improvement and collaboration over this challenging problem. I will show you all the details at the end of my presentation. What we have done is we have designed a novel and powerful methodology and application for increasing shopper behavior analysis with relevant application in marketing and customer research field, with a particular focus on increasing customer understanding. The RISE framework, we call the RISE framework at the name of our laboratory, is developed to deal with 3 important tasks: people counting, shopper analytics, and identification. In particular, people counting is devoted to segment and count people with high accuracy, more than 90%, even in crowded environment. Shopper analytics is devoted to measure and classify interaction between shopper and shelves with a good accuracy, also compared with cashier sellout. And the identification is devoted to recognize customer inside the store over contemporary shopper, up to 1,000 people in the same area at the same time, with a good accuracy to detect massive behavioral data on the best performing category, more than 80% with 100 or 250 contemporary shopper in area. In order to cope with this multimedia task, current models, including their architecture, training, and intermediates, must be adapted or even redesigned. This system has not to be only reliable, but also cost-effective in order to maintain scalability, but efficient enough to run on the edge. This network that we have designed uses the same data stream and a common preprocessing phase that produces a proper input for each network. We choose the top view identification, the top view RGB camera, and why we choose the top view RGB? Because the top view is privacy preserving, because the page is never recorded by the camera. Moreover, the other important feature of an RGB camera installed in this particular configuration is that this configuration prevents the problem of fusion between people, especially in a very public environment. So it was RGB camera for our goal is to better the solution, especially in the environment. The first task, as I said, the first task is the devoted to people, so it represents people. The tracking people is a challenging task in a persistent crowded environment for behavior analysis. For example, but also we can think to airport station and so on. What we have done is that we are using an approach to track and detect people in the presence of persistent and temporary occlusion with a convolutional network for semantic segmentation using top view RGB data in a crowded environment. The top view as dataset is a dataset of that images that images captured from an RGB camera installed in a top view configuration. The images collected in this dataset represent a crowded environment with at least 3 people per square meter and physical contact between them. We have designed a new network called specifically designed for this task. This network is devoted to segment and count people inside a very persistent crowded environment. As you can see, the result is 90%, so a very accurate approach for counting people, especially in crowded environments. The second application regards shopper analytics, a tool developed with the T-Lab and probably about it later on in the presentation. But the idea is we have the same camera and a top view configuration installed above the The shopper can perform three different interactions: positive, neutral, and negative. Positive dot green, neutral dot yellow, negative dot red. Positive, shopper pick up the product. Negative, shopper pick up the product and put it back. Neutral, the shopper accept the product. The red dot is the most valuable information because the retailer don't have this kind of information, neither on the cashier sellout. We have collected dataset even in scale. This dataset is called a dataset that is composed of more than 10,000 manually labeled frames. This dataset was acquired in a real retail environment over a period of 3 months using 7 different cameras located in 4 different shop categories: chips, women care, body care, and spirits, above a total of 10 shops. Frames were labeled in 4 frame interaction classifying classes. So we have a positive, neutral, and negative images, and negative classes, sorry. Positive contains images that show and or the product. Negative is the class that contains images that show only an end. And neutral contains images in which the customer is not interacting with the chef. Moreover, we added another class, the refill, which is composed by images that indicate a reflection, which happens every time a box filled with product is equal. This class, the class of refill, has a priority over the others. For instance, if there is an end or a product and a box containing the same product with the same image, the class is the needed refill and not positive. Even in this case, we have designed a new network, the Brightnet2. This network was designed to have efficient architecture for classifying shopper interaction, and this network can be also readapted to classify either 3, a negative, neutral, and positive, or 4 negative, neutral, and positive classes that can be modified in the last layer. Even in this case, the results are really satisfying with either really satisfying with the really high accuracy. The last part of our framework is devoted for shopper identification. In a common real-world application, a watch list of 4 people is given and the gallery target set for searching through a large volume of video recording location where said people are likely to return. This aspect is really fundamental in retail to understand how customers value their shopping. The identification of regular and occasional customer allows temporary purchasing profile to be defined, which can correlate customer temporal habits with other information such as the this knowledge enables novel marketing strategy tailored to the more temporal and systematic behavior of each customer, as well as innovative services and increased customer awareness based on shopping schedule conditions. Even for identification with the dataset, above you personal identification tool dataset, this dataset was composed of 255 videos containing RGB channel and left channel. Each video recorded the people on the forward path, left to right, for half the time, and recorded the same people on the returning path, right to left, for the other half of the time, through not necessarily in that order. The number of people present in the videos varied from 1 to 11. The total number of people in this dataset was more than 1,000. Even in this case, we have designed a network. This network is called Brightnet3, and Brightnet3 was designed for understanding the important statistics of the shoppers, which included the time spent in the store, the product chosen by the customer, and the shop attraction time. The approach recognizes people from RGB images and consists of 2 steps: person detection and personal identification. Moreover, we have another important feature, which is the temporal part, which is really important to understand and to recognize people inside the store. It can be said that even in this case, Brightnet3 is in in all metrics the performance of the other feature bases. Moreover, we have also complete and we have also solved a more realistic identification settings using top-view open world personal identification. In fact, in a common real-world application, a watch list of known people is given as a gallery target set for searching for a large volume of video where the people on the watch list are likely to return. The approach is based on a price range convolutional neural network, and a triplet loss was used to train this network. The triplet loss optimizes the embedded state, like data point with the same identity are closer to each other than those with different identities. The results show that the proposed methodology is readable and accurate over time and advancing the state of the art in field. We have concluded their framework also by evaluating the weight of software to understand if its preferences are for healthy or non-active food. We adopted the same camera in a top-view configuration. The interest relies on contextualizing the body weight measurement in an unsupervised and comparative framework in which the subjects are not requested to provide any explicit input to the measurement system. Furthermore, the approach has to be included does not imply, for example, the need to set over a specific device as well as going through predefined gates in which the measurement is taken based on the presence of a dedicated visual system. The very way more than 1,100 in configuration, and the deep neural network has been trained on this that data. We achieved the results, demonstrated the suitability and the effectiveness of the solution, showing good results, especially when the architecture lacks denseness and efficiency. But what we are doing now? When people work in a space such as supermarket, they are to a huge number of unwritten media groups and observe social practices. For instance, if they move inside a space, they respect the personal path and allow other nearby people to have their right of way. The competence to model these unwritten rules and apply them to understand and generate user movements in an environment is extremely worthwhile to design an intelligent rating system in a smart environment. For this, we have studied human trajectory prediction, because human trajectory prediction is an important topic in several applications, ranging from self-driving cars to environmental design and planning, from social aware robots to intelligent systems. This complex subject comes with different challenges, such as human-space interaction, human-human interaction, multimodality, and general applicability. Currently, these challenges, especially general applicability, cannot be completely explored by state-of-the-art works. Some of these works are listed in the slide. The most famous are social life STM, LSTM, or the social GAN. We are focused in our research on the prediction and generation of human trajectory via predictive and generative models in a specific environment, but in particular, the complex goal that we are facing with this study is in a complex environment with complex constraints. For this, we have collected 4 datasets from 4 different sources in Germany and Indonesia. We collected in 2-year period in which of the behavior more than 10 million shoppers and been measured. The data has been collected with a trading system based on ultra-wideband technology with tags embedded in store cards and baskets. The ultra-wideband technology is suitable for applications where the position of accuracy is a critical issue. This technology provides the use of several ultra-wideband antennas properly positioned inside a predetermined area and powered battery packs with the inside this area. This has been used to deploy a real-time operating system, RTLS, which gives completely oversight of the customer and employs the store and improves the customer experience. experience. This dataset that we can share with you is a publicly available dataset. It's called the shopper trajectory dataset. It contains more than 1 million shopper. In our work on this pattern recognition, we have proposed and defined new methods and methods to understand trajectory. In particular, new deep learning model based on long-term memory and generative network architecture are used both in both communal and industrial. These approaches are evaluated with new error metrics, which normalize unbiased standard metrics. Tests have been assessed using newly collected data characterized by higher diversity and lower linearity than those used state of the art. Because we compare both the results with, for example, APAs, UZY, these datasets are linear trajectory. Instead, our dataset is characterized by a higher diversity and a low linearity. The results prove that the proposed model and dataset are comparable to yield better generalizability than state of art work. Moreover, we also prove that our dataset better represents multimodal scenarios, allowing for multiple possible behaviors, and that one trajectories are moderately influenced by their spatial region and slightly influenced by their space content. We have continued our approach by employing a generative personalization learning framework hybridized with classical reinforcement learning methods. An example of classical reinforcement learning methods uses the continuous penalty, which allows the model to shape of the trajectory and to insert a bias, which is necessary for the generation training. The structure of the framework and the normalization of the problem to be solved allow to evaluate the results in terms of generation and prediction. The guide framework has been used for modeling trajectories in the retail environment. This work allows for both generating trajectories from scratch and predicting from trajectories that have already begun in order to predict the future pattern of a person. The system provided is also very general, and the data can be constructed in multiple ways. Depending on the user reward, we can either enhance or regulate the behavior of the one bit. And this slide shows some example of the generation of the trajectory inside a real store with the real map and the real layout of the store. With such a framework, we can create a store simulator, which is our goal, where we can predict the customer behavior with different layout, shelf position. Moreover, combined with the shelf management, the application of working lab that will be presented by Rocco, we can monitor care for understanding what happens in the shelf. So thank you for the opportunity to share our research in the field. You can find data and source code to ensure comparison with the code methods and future improvement as collaboration over this challenging scenario. So if you have any question and if you want to know some other important details of our research, please ask me. Thank you.
Let's see. Marina, are you with us?
Yeah, I'm here with you. Can you hear me?
Yeah, we can hear you very well.
Yeah.
Any questions?
My voice is not completely clear over Zoom, but I know my research, so unfortunately, probably the attendants over Zoom cannot hear very well the presentation, but don't worry on that.
Any questions from the crowd or from home? Okay, so I wanted to ask, general, are there any products that are being deployed in supermarkets nowadays based on things that you've shown, or is it more a research phase?
Sorry, I don't hear you.
So I'll try again, and then we'll see what we can do.
Yeah.
Are there actual products based on the things that you have shown in supermarkets, or is it more research?
No. These are all tools already developed. These tools are installed in real scenario, in real supermarket. The dataset that I show you contains dataset collected in real retail environment. All this kind of information can be, we are share all this information with you because the dataset are publicly available. Probably Rocco during his presentation will tell you more detail about our installation, because this installation is a collaboration with the Grottini Lab and with other important companies. So our tools and our application are already installed in a real retail environment, not only research.
Cool.
I'm also a researcher, so I combined these two important aspects of my work.
Well, okay, we have a question from the crowd.
So I have a question, great talk, by the way, thank you. And then for the HADA data set, so did you detect the hand from the RGB data set? RGB or from the image or RGB, did you detect the hand in the other product to classify, you said empty hand or hand with the product in other situations?
I don't understand very well because the voice is not completely clear, but I try to reply to your question because our application, Shopper Analytics, is an application developed in collaboration with Grottini Lab, and our dataset is composed by RGB images. Images for that contains the hand and the product in that images. And we classify these images basing for the hand. So product with hand, only hand, and images without hand. And we consider these three kinds of interaction because it's really important to correctly classify the interaction, shoppers interaction, how the shoppers interact with the shelf. So we try to monitor, we try to analyze all this kind of information, starting from an RGBD camera installed in a top view configuration, and all this information are privacy preserving, as I already said during my presentation. And we also, in this case, we use only RGB images, but we in other application, for example, people counting or identification, we use also the depth channel. So here is the main reason of why we use RGBD camera.
Thank you. So I'll ask one more one, but I'll use the chat, so it will be perfectly readable. So my question is, when looking at the data of the person trajectory, and also write it down, did you see anything, any insights that the retailers found surprising? So write it down as well.
When you talk about some insights, not because we monitor only the trajectory of the customer, we use some important simplification, because when we talk about trajectory, we consider shopping the tag installed in shopping carts and basket. So we monitor the human trajectory, the shopper's trajectory with this tag installed in shoppers carts and basket. And monitor this trajectory and collect this huge data set of trajectories. All the data set that I have mentioned during my presentation is publicly available. So if you want to collaborate, if you want to continue our research, continue with us this kind of research in this field, please contact us, me and Rocco. And this data set is used at the beginning for understanding which is the mission of the store, because each store has a mission, as our colleagues of the marketing has explained to us. But now we consider this trajectory for predicting and also for generating a new trajectory, because it's really important for our aim, which is build a sort of store simulator. And now with the generative neural network, this can be possible.
Okay. So thank you for joining us.
Thank you for the invitation.
No problem. So we'll take a short break until 11:40, and then we'll have another session and then we'll be done at 1 o'clock. Mhm. אני יודע טוב כמוך. לא, יש לי מאפין לכל היתר. באמת? בינתיים אני בסדר. Rocco, do you know if there is any good coffee around the city?
I don't know.
We have 10 minutes. Yeah, I think we're going to.
Yeah.
So it's good if you have enough time.
Yeah, the thing is that we sell data about our business, so actually we don't get back what we want to do. So, the more it affects shelter, and then they change the layout, so we know that they change the layout. Usually the reason that we want to change the
Yeah. Do you know artificial color? So I'm wondering the average time how long it takes to finish.
Yeah.
Is that kind of data?
Yes. It's kind of data that we want to obtain from the shelf analysis.
So there will be some data. One of the something that you could buy.
I don't know if at the moment right now they are saying going well because we have a big project running, but they are more interested in the software of the shelf.
Yeah.
So that's basically the only thing they care about, and the shelf. So nothing else seems to be.
Yeah.
Shelf and the same.
Yeah, for us, the first part is a CPG company, where they want to know the trust is organized properly. And then basically we started to work with the retailers, retrofit in the stores with the camera, taking out the stop alert and so on. And yeah, they don't care about, they only want to know the prices of the which products are the stock, how long they shelf. So it won't be
we have a long tradition with the out-of-shelf detection. We have it for vision. We love as a contractor, but we use some of sensors that we use to place on the shelf. So we install a bar, with sensors, and the sensor is a proximity sensor in the presence of the product. It's platinum is not inspected. At the beginning, this was used around the morning on the shelf, and also the time of the fill. So how long is the shelf?
Yeah, I probably don't have all the
Yeah,
but they're very helpful when they're not correct.
Yeah, no, I'm not.
No, because Chinese select.
It says like $100 of the entry fee.
Yeah.
Just need to register, get a number.
So why do you have special fund?
Nice. And that's the optimal.
Oh, it's very good.
See the lighting bulb. I just put it here because when I put the pins, then it's a little bit weird, disrupting my design.
Why is it complicated?
Basically, let's step away from the microphone because it picks up everything. The concept is that company suggested name. Basically following your footsteps.
How long does it last?
It's supposed to be 9 hours. If you notice that when I was booking the flights, 9 hours is crazy. But then the flight was postponed by 6 hours. So I ended up spending all day from the morning to evening at 4:30 a.m. And eventually flew out at 6 p.m. So I spent almost the whole day sitting in the took over. Finished up the presentation, so actually time well spent. Should we get started?
Yeah. Okay, so now begins our last session for today. We have Boaz Arad from Oddity. Let me see. Please note that the screen is recorded, so it's possible that
You might be seeing the presenter.
Yeah, is that
That's
okay?
fine. Yeah.
Fine. Okay, so go ahead.
Hopefully they're seeing the correct presentation, but if not, I'm sure they can deal with the presenter view as well. So hello, everyone. My name is Boaz Arad. I am the Chief Vision Officer for Oddity and a co-founder of Voyage 81. And what I'd like to share with you today is a bit about what we've learned during the past 3 years about cameras and how understanding them can help you when you have fine-grained recognition or matching in mind. So just before we start, a word or two about Oddity and what we do at Oddity. So Oddity is a tech-centric company. We are a house of brands, and today we have 2 brands which you might recognize and a third one on the way. Our first brand was Il Maquillage, launched in 2018. It is a makeup company. It focuses on complexion products and started out even back in 2018, matching people with their correct foundation makeup using only an online quiz and getting very high accuracy without actually ever seeing people. Now that we've added vision into the mix, we're working on that as well. The second brand launched early this year is Spoiled Child. It's an anti-aging brand that has a wide variety of products from skin creams all the way to hair products. Really excited about that brand, started using their products as well. That one has a little bit less vision in it. And finally, brand number 3, which I can't share too much about at the moment, but I will say it has to do with skincare. It borders on medical applications, and it's going to be very vision intensive. And this is something that is taking up a lot of my time and my team's time. We're working on building out the vision applications for brand free. But I won't tell you too much about what we do at Oddity other than this. And I do want to focus on what hopefully is going to be useful for you. And that is how we can understand cameras and what you need to know in order to make them more accurate and better calibrated for very, very specific applications. So I'll start out with a little bit of background. Anyone that's been following the science of computer vision for the past decade or 2 has probably noticed that things have just progressed in leaps and bounds, and we're doing things today which we would have never thought possible 10 years ago. And I think automotive is a great example for that. We're seeing these driver assistance systems, self-driving cars, doing things like identifying vehicles, pedestrians, road signs, drivable areas, non-drivable areas, obstacles, and doing this at very high accuracy, real time, super impressive stuff. So this is kind of a tour de force of the vision science today. But I think for a lot of the people in this room, the problems that you might be dealing with day to day look more like this. And if I show you these 2 cars and ask you what's the difference between them, I'm guessing you would tell me, well, the car on the left is red. And you're of course correct, but the difference I was looking for is that the car on the left is a 2022 Model 3 Tesla and the car on the right is a 2021 Model 3 Tesla. And the algorithms that we've been using to do things like differentiating between vehicles and pedestrians are very, very ill-equipped to deal with these types of problems. And you could even say that they are geared towards ignoring them. We care about differentiating between a vehicle and a pedestrian, We don't care if the vehicle is even red or white, not to mention what year or model it came from. And of course, in the beauty and wellness sector, we are very, very intimately acquainted with these types of problems. In Il Maquillage, for example, we sell over 60 different shades of foundation makeup. And the reason we sell 60 different shades is because there are at least 50 different classes of skin tones and 50 different types of skin, which each needs its own unique foundation color. And if our customer is going to receive the wrong foundation color, of course, they're going to be unhappy. So we need to very, very accurately match people with their correct products. And of course, I'm guessing most of you aren't in this industry, but perhaps more towards retail. And this is just another example, which I borrowed from my good friends here at Trax. Imagine trying to identify specific products from a chaotic setting like the one on the right here, low resolution, confusing environment, and you're tasked with not just identifying something as a shampoo bottle, but you need to know the very specific type of bottle. And what I love about this slide is that you can see on the left several products. Each one of them is an actually distinct product. They look nearly identical, but they are not. This is the difference between different shades of hair mousse, different types of shampoo and conditioner, or combinations of them. This is, I think, confusing even to human shoppers. And we really want to be able to identify things like this with very, very high accuracy. And what I'm going to focus on today is the topic of color. And to kind of give you a feel of the problem here, I set up an experiment in our home office. I put up a little mini studio, I put a can of diet soda in it, and I asked our employees to just take a photo of this soda can with your smartphone and email me the photo as is, out of camera. And I got 14 different photos, and I took a look at the same area on that soda can in 14 different photos out of 14 different cell phone cameras, and I got 14 different colors. And let's see how that looks on the projector. It's a little bit difficult to see here, but that's why I set up the two most distinct colors on the right. There's really a huge gamut of colors, a huge variation between different cell phones, looking at the exact same objects in the same conditions. This was an internal room with very little ambient lighting, so just the same illumination, same background, same object, nothing there that could confuse the camera. This is really the ideal, optimal setting you'd expect to be the most consistent that you could be in a setting like this. And this is, of course, what you get. And if you're trying to do very, very accurate product matching or product recognition, this simply won't do. You need to be able to trust your camera, you need to be able to understand the data that you're receiving. And if your machine learning model has to deal with this type of noise on top of everything else, you're probably going to have a bad time. So let's dive into why this happens. And to do that, I need to talk a bit about the imaging pipeline. And what you can see here is a rough approximation of how an image is formed in your smartphone. You have an object, light is reflected off that object, it goes through the lens, goes through the color filter of the camera, goes to the image sensor, photons are then converted into electrons, that's read out into an image signal processor, and finally you get your bits into your machine learning application, and then you have an image which is machine readable. Now, the ISP does a lot of things. It will try to correct colors, it will try to enhance contrast, reduce noise, improve the just kind of the human perception of quality in the image. It does a lot of things. And if your vision application is stuck behind the ISP, if you have no control over the images that you're receiving, my first piece of advice would be, well, maybe don't do that. I strongly recommend, if you have the ability to do it, turn off the ISP, get raw data directly from the camera sensor, or at the very least, control the ISP and make sure that you know what it's doing and you have control over the parameters, things like white balance, things like noise reduction, that way you can prevent a lot of destructive editing and you're going to have much more consistent images. If you are stuck behind the ISP and there's nothing you can do about that, then I will point you towards some interesting work that's been going on at Google. They're doing things on image unprocessing, trying to kind of reverse all the damage that the ISP is doing. But I won't get into that in this talk. And for the purpose of this talk, let's assume that you have something like a native app, you have control over the camera, and you are able to either control the ISP or completely disable it so that you're just looking at the bits out of the sensor. And that's a much simpler setting to be in. And it's not that difficult to get to that point. All you need is a native app. Or of course, if you're working with scientific cameras or industrial cameras, then you have full control, and that's great. So in this case, we only have to deal with the optics and the image sensor. And again, we're assuming that we're getting light reflected from the object, going through the lens, going through the color filter array, hitting our sensor, and finally that is being read out into our unprocessed image. So let's look at a single pixel in this setting. What happens with a single pixel? That pixel is reflecting light in many different wavelengths and different intensities. There's this distribution of light that's coming to you from the object, going through the optical path, and that is finally translated to the color that you're going to see in the pixel that you're observing. Now, of course, the lens has its own attenuations, the color filter has its response function, the image sensor has its own sensitivities, but you can just kind of group all this together and describe it with an observer function. And what this observer function does, for those of you who aren't familiar with this type of formulation, it just quantifies the intensity of the response in each color channel of your camera based on the amount of light coming in each wavelength. So you know that the blue channel is going to be much more sensitive towards about 400, 500 nanometers. The red channel is going to be much stronger, around 600 nanometers. But you really don't have to know a lot about the physics here, just basically understand the concept. And if you know the distribution of light that is coming to the system, this is just simple multiplication, and you can take the distribution of light coming in, multiply that by the sensitivity in each wavelength, and get the exact output that that system is going to give. And there is one more wildcard in this setting, and that is illumination, because you're not just looking at light that's being projected out of an object, but rather you have a distribution of light coming from whatever's illuminating the scene, hitting the object. That object has certain absorption properties, reflective properties, and it will reflect that light to your camera. And this is finally kind of the complete system. You have the distribution of light hitting the object, the way that that object reflects light at different wavelengths, and the way that your system responds to light. And again, this is just simple multiplication. You can end up with the exact response you can expect from your imaging system. So now we have a rough concept of the imaging pipeline, and this is something that we can very, very easily model if we have the information we need. But of course, I'm guessing that most of the people in this room have not worked with this type of information. You haven't been doing these modeling. So let's talk about how you can get that information. The easiest way to do it is with a hyperspectral camera. And what hyperspectral cameras do is take an image of a scene very similarly to a regular RGB camera, but they will provide you with the amount of light in many different wavelengths. They will give you a graph like the one on the right here for every pixel in the image, which is really neat. It's a lovely tool. Downside is these cameras are expensive. They cost $10,000 or $20,000, and they take a long time to collect a single image. They can take seconds, if not minutes. So this is not something that you want to be using in a practical setting. But fortunately, there are people that have these cameras and provide data sets and have made these measurements. So these are measurements that are not very difficult to get if you need them. And we have a camera like that. And we've collected such a data set. We've actually shared some very large data sets of this type of information. But before I go into that, I do want to show you what happens when we apply what I've shown in practice. And here what you can see is a scene that we've collected with a hyperspectral camera. And we've applied different illuminations to it, and we've applied different camera responses to it. So you can see on the top, we have a Nikon camera, on the bottom, that's a Canon camera. This is fully virtual. We applied the imaging pipeline as you've seen before.
And you can see that we see that exact same effect. We see that the same point in the same scene, this is a pixel perfect image. It's the same image collected with a single hyperspectral camera, computationally simulated to be coming out of a Nikon camera and a Canon camera under different illuminants. And these illuminants, for those of you not familiar with the CIE notation, A is artificial light, like incandescent light bulbs. D50 is going to be outdoor illumination, sunlight, and F2 is a specific type of fluorescent. So you can see how the image will change based on illumination, based on the observer function, which is the only difference between the top and bottom image here. And you can see how different those colors are. And here again, another example, which incidentally contains a can of Diet Coke. Sorry, this is non-Diet Coke. And we can see that effect that we've observed earlier. And by the way, fun fact about products like Coca-Cola. Companies like Coca-Cola spend a lot of time and money making sure that their colors are super consistent. And they do that to the extent that I've met people that use these as ad hoc calibration objects. If you have a camera in the field and you suspect that the calibration is off, you don't have a professional color checker on hand, run to the shop, buy a can of Diet Coke. That color is going to be consistent across copies, across countries. It's a very specific Pantone. It might be even better than an X-Rite color checker. So a great reference object. And you can see here that even though I took the same frame from a hyperspectral camera, just changing the observer function is going to create pretty significant differences. So I mentioned that we have collected a lot of data like this, and I'll take the opportunity to invite you to see our talk later today at the entire workshop, where we will be talking about the data set that we've just released, the largest ever of its kind, over 1,000 hyperspectral images. And that is one possible source for hyperspectral data like this if you don't want to worry about collecting it yourself. The second thing that we cover in this challenge is recovering this data from non-hyperspectral cameras. But I won't go into that in this talk. If you like, I'll put up the schedule later. The second thing that you need in order to do this type of modeling is the camera function. You need to understand the observer function. And there are 3 ways that you can go about that. One is measuring it yourself. And that's what we do at Voyage 81. We have a tunable light source. It's a very expensive and complex system that can produce light in very specific wavelengths. We'll put a camera in front of that. We'll run it through the gamut of different wavelengths, and then come back with a very highly calibrated camera function. Of course, you probably don't want to do that. There's quite a learning curve. So what you can do instead is go to an external service. There are other companies that will do this as a service for you. You can get your camera calibrated. The guys at the European Machine Vision Association, the EMVA, actually have a standard in place called the 1288, which asks vendors to declare that, and you can send a camera out to be calibrated based on that standard. Another fun fact here is that when that standard first came out, and suddenly companies like Sony realized that they were being measured, they knew, but we started noticing that cameras were very inconsistent. The response function of sensors was wildly different between the center of the camera and the periphery. And the minute that companies like Sony started realizing that people were actually measuring this, they started tightening up the quality process, and they started putting out better cameras. And that brings me to the third option. If you need this type of data, ask your vendors. You're working with a Sony camera, ask Sony. You're working with a Basler camera, ask Basler, OnVision, OnSemi. Talk to them, ask for this information. The more people ask for it, the more the vendors are going to care, the more they're going to pay attention to the camera calibration, make sure that copies behave the same way. It's going to benefit our industry as a whole, even if you're not doing any of this. So ask your vendors, and a lot of them are already publishing this information. So that brings us back to the camera model. And in order to do this type of modeling, we need to know these 3 things. We need to know the observer function, we need to have a calibration for our camera, we need to know the reflectance of the object, and we need to know the illumination. So the observer function, hopefully you send an email out to Sony, they send you back the sensor properties, you're good. Object reflectance, you can measure that. And the nice thing about this is you need to measure it once. Once you've measured it once, you know that forever it's a physical constant. That's fine. Illumination is a little more tricky, but it's not that complicated because whatever you're doing, even if you're in a very varied setting, you're going to encounter only so many illuminations. So imagine, let's say, a retail store. So you're going to have artificial lighting, maybe several types. You might have some ambient light coming in from the windows. So you might have different kinds of daylight, but how many different illuminations are you going to see? 10, 20, 50, maybe 100. Point is that this is bounded. There is a limit to the amount of different types of illumination that you can expect to see. And now what you have is essentially a well-defined space of what color a certain object can occupy. And to kind of touch on how that helps us, there's an example I love to use from the time that we were in the automotive business. When Voyage 81 started out, our first target market was automotive, and we were trying to help companies like Mobileye identify difficult objects on the road. So driver assistance, self-driving cars, things like that. And it turns out that tire debris are a huge problem. They are the #1 object that vehicles collide with other than other vehicles. I think they're responsible for about 10% of object collisions on the road. And looking at these examples, anybody that's done computer vision can probably imagine why they're so difficult to avoid. They don't have a consistent shape. If you can see the texture of the tire, it's too late, you're too close. They are very similar to other confusing objects on the road, such as manhole covers, shadows, patches on the asphalt, stains on the road, very difficult to see. And of course, black on black, they do not stand out. So kind of conventional computer vision, looking at a lot of examples, feeding a neural net with many tagged samples is not going to work great. It will work eventually, but it's quite difficult. But imagine that you've taken, you've had thousands and thousands of hours of road video meticulously annotated, and you fed this into your machine learning algorithm, and you're getting good performance on recognizing tire debris. Is great, you're golden. But then I'll ask you this question. Could a tire debris be bright pink? Can that happen? And of course, when I found up this example, I had to check, and obviously somebody made an actual pink tire. This exists. This was done as a breast cancer awareness promo. But for the sake of argument, let's imagine that we're talking about standard automotive tires. And we want to identify standard automotive tires. And obviously anything bright pink does not fall under that category. So you have this neural net, 99% accuracy, you're really happy. And then I ask you, what happens if I show it a bright pink object? And there are two options. Best case scenario, your network has spent a lot of compute resources, a lot of network space has been used to kind of understand the concept of tire debris. And you now know that tire debris have more or less a black color and they cannot be bright pink. Worst case scenario, there aren't a lot of bright pink things on the road at all. And if I show your network something that's bright pink, it might think it's a tire debris, and it might think it's a pedestrian. It might go crazy because it hasn't had the chance to understand that concept. But going back to our camera model, it turns out that automotive tires, no matter where they come from, are pretty much built out of the same type of rubber. And it's a material with a very constant physical spectral signature. So that is literally a constant. And if you know the calibration of your camera, then of course, and if you're selling a driver assistance system, you definitely know that calibration. The only unbounded variable that you have here is illumination. And again, even if you're driving a car anywhere, there are only so many illuminants you can encounter. And that allows you to formulate the problem in a way which is bounded to begin with. And there's always this ongoing debate on whether we should be handcrafting features or letting our neural nets just go crazy and learn everything themselves. I'm not getting into that, but what I am saying here is take the opportunity to try and formulate problems in a way that encapsulates this type of physics in. You can formulate the problem in a way that allows the object that you're trying to identify to only live within a well-defined space. And then you can either handcraft features on top of that, or you can let the network learn its own features, it doesn't matter. But to begin with, you have made the problem smaller. And that translates into less compute time, higher accuracy. You'll need less examples to train your system, and hopefully things are going to work a lot better for you. And just to kind of wrap up, I want to show you an example of how we've applied that. And this is kind of going back to the health and wellness sector. This is something we did in Voyage 81 before joining Oddity. We were looking at melanin and hemoglobin. Hemoglobin is a blood component, and melanin is a pigment which gives your skin its color. And both of those things are very important for diagnosing various skin health issues. And if you open up the literature, the reflectance, the way that these things absorb and reflect light, is very well studied. And here there's a graph which I pulled out of a paper on skin health. And we went about and used this type of modeling to try and see if we could identify and map the amount of hemoglobin and melanin in someone's face using just an RGB image. So we're not using a hyperspectral camera here at all. And we were successful. And when we started out with this project, we did what we often do in projects like these. We started out with a hyperspectral camera and created a virtual camera model to try and figure out if this is even feasible. We had good preliminary results, so we went on to apply this to an actual physical RGB camera, and things looked good. We were happy, and then we went and tried to apply it to video. And when we started doing video, we saw that the hemoglobin maps became unstable. And this has happened to us before, and usually it means that our training wasn't perfect. Some edge case kind of creeped into our model, and it became unstable, and we were trying to diagnose this instability. And we couldn't find it. We couldn't figure out what we did wrong, how the model was kind of flaking out. And we were pulling hairs at this point until one of the engineers said, wait a second, what happens if we plot this over time? And you can see that on the left here. And what happens is that we can correlate this with the user's heart rate. And of course, as blood is pumping in and out of your face, the amount of hemoglobin is changing, and this was actually physically happening. And we then took this and turned it into a system that could remotely measure someone's pulse, or even multiple people, with just a regular RGB camera based on the hemoglobin content that we extracted. So that was a happy accident, and we might be coming back to this in the future. But to summarize here, I think the main takeaway from this presentation should be try not to learn things that you already know. Anything that you can take away from the space that the network needs to operate in, anything that you can do to make your problem smaller is going to make it easier. And you know, hopefully some of you are going to go back and look these things up, open up some hyperspectral data, start doing observer function modeling, and you're going to improve your networks. I'm guessing most of you won't, but if you take away one thing, one practical piece of advice from this talk, if you're doing anything at scale with many, many different cameras, try adding the model of the camera as a parameter to your inference network, to the input of your network. I guarantee you, if this is happening at scale, it will improve your performance, because that will at least allow your network to understand that these are different phones and they're going to behave differently, or different cameras. And the more you can do, the better your results are going to be. Try to figure out, maybe this camera has a bit more blue than the other one, and you're going to be able to either correct for that manually, or at the very least, add that as a bias or a hint to your machine learning system. And finally, I'd like to thank my amazing team at Voyage 81, some of which are here with me today, and you're more than welcome to catch us in between sessions. We usually love to chat about these things. And if you do want to hear more about how you can get hyperspectral data even if you don't have a hyperspectral camera. We do have a session in the entire workshop later today, and we'll be touching on that. And you'll be happy to hear that there's quite a few papers with code that do just that. So I think that's it. If you have any questions, I'd love to take them.
So compared with the traditional RGB, does the hyperspectral help with noise rather than getting very noisy and put it out onto the ISP, tend to try to remove that? Hyperspectral makes that.
So that's a complex question to answer, because if you're using an actual hyperspectral camera, that would introduce more noise, but simply because if you're trying to measure the amount of light in each wavelength, you need to use essentially optical filters, which are very narrow, which means you're getting a lot less light to the camera. So getting a hyperspectral image with a hyperspectral camera is a much more complex endeavor than using an RGB camera, and you're going to need more light in order to get the same noise level. But in practice, I think that if you're working with hyperspectral information, and I think the more correct way to look at this is, let's say you're trying to do something like recognize tire debris. So you're going to take the hyperspectral camera and you're going to photograph a few tires and in a good calibrated setting, and then you're going to use that as a reference for working with your RGB camera. And if you have a good concept of how your object behaves under different illumination conditions, that can allow you many times to kind of differentiate between noise and variance between objects. So it makes things more explainable, because noise will usually be evenly distributed, or you can model it, and then you can kind of do simple things like maximum likelihood. Is this change more likely to be due to the fact that I'm looking at different objects, or is it more likely to be due to noise? And that's the way I kind of like to look at hyperspectral as it applies to noise. I hope that was helpful.
Question for your great presentation.
Thank you.
If we have a hypothetical situation where we have fully controlled noise, there's no noise in that. And we have one hyperspectral camera looking at two different objects. One is made of nickel, other one is made of iron. Can the hyperspectral camera somehow help us identify material in
Definitely.
a very controlled environment?
Definitely. And even in not so controlled environments. What we did at Voyage 81 back in 2019 is we were actually able to differentiate between rubber tires and asphalt using just an RGB camera based on the hyperspectral data we collected previously. But that's where hyperspectral imaging came from. And actually, it's kind of funny. I've never given a talk about hyperspectral without that introduction. The whole idea, this comes from spectrometry, this comes from chemistry. The idea is that if you can take a calibrated measurement, you can not only differentiate between materials, but you can many times understand the composition of something. So you can take a photo of, let's say, a soda, not the can, the actual liquid, and figure out how much sugar there's in it based on how it reflects light. And of course, that's very difficult to do in a noisy environment if you don't have a hyperspectral camera. But in a low noise environment with hyperspectral systems, definitely possible.
Yeah, just an point, we have been working for a while. We are using hyper frequency sensors, but hyperspectral imaging can help with that.
Definitely.
Control the environment.
Definitely. I'd love to catch you offline. We could discuss.
First of all, fantastic talk.
Oh, thank you.
So I want to mention several tips for using this RGB cameras. One would be to use a raw image if possible, turn off the ISP, and the second one to input the phone camera parameters to the machine learning model. What other advice would you give for using this? So using a phone camera for this type of stuff, say I want to identify the tires on the road, like using my phone camera, so no hyperspectral sensors.
So I think we'll touch on that also in the entire presentation, but basically, if you're able to model these things, for example, to take the example of rubber and asphalt, these are things that might appear similar, then you can use this type of camera model to figure out where your RGB camera might see the exact same color. Asphalt and rubber can be the same color. There are cases where this can't help you differentiate, but you can understand what the space is where they are different. So that's one thing that you could do. And I think I'd need a more specific application to be a bit more specific than that.
If say you're in a store.
Just we have like 1 minute, so if you can.
Differentiating between, say, cans of Coca-Cola.
I think the best thing would be to understand how your different targets behave in whatever camera you're looking at, and you can get a lot of insight from that. And if you'd like, we can talk offline, and I might be able to kind of find a more specific answer.
Sure, great, thanks.
One thing I will add, though, is that I've only scratched the surface of the various things that ISPs and image sensors do when they process the image coming out. They will have nonlinear behaviors. The more you look into this, the higher accuracy you can get. And I'll hand it back to Ellie here. Sorry for running over time. And thanks for hosting us.
Okay, so now we have the talk by Rocco Pietrini from Grottini Labs. Okay. Is it okay if the presenter view is recorded?
Yeah, it's okay. Good morning, everybody. My name is Rocco Pietrini, and I'm a deep learning engineer in Grottini Lab. I want, first of all, thank you for joining me in this presentation, and I want to thank the organizer of this workshop for inviting me in such a great place. Today, I'm going to talk about the dynamic shelf management, what are the deep learning opportunities and the future challenges that are in this field. So as I said, I work for Grottini Lab, which is a company located in central Italy on the East Coast. I will tell you a little bit more later. So the agenda is an intro of Grottini Lab. Then I will talk about what does it mean that the shelf is dynamic. I will talk about our shelf management system, what are the challenges and what are the next opportunities. Basically, in this talk, we'll see applied most of the research ideas that Marina told you before. So as I said, Grottini Lab is a tech company, is a young company that has as a core business to monitor, analyze, and improve what happened at the store level. So basically, we try to understand the shopper behavior inside a real store on a different levels. So this is the team that I want to thank you for letting me participate here at this event. Let's start with a little bit of application. We started with the shopper analytics. Marina talked about it a little bit before with some research ideas. Basically, we use RGBD cameras in real stores. We use a camera to monitor what happens when you are in front of a shelf. So we install cameras in existing stores, so the impact is minimum. And we have a discrete installation on the dropped ceiling. We choose the top view because we can minimize occlusion. And thanks to the depth channel, we have a 3D perspective of the scene. So we can exactly know where the interaction is happening. We can see from here that we classified interactions in 3 different ways. So positive interaction when you take something out of the shelf and you see a green bubble on the product. a negative interaction if you put something back, or neutral interaction if you just touch something, and we have a yellow bubble on the product. As Marina said before, the negative interaction is the most important one because you don't have this data from the cash flow data. But for example, if a product is often picked up from the shelf, but always return it back to the shelf, maybe there is something that is not convincing the client to buy the product. So this kind of data is really important from a marketing perspective. Then we can, of course, count the number of people passing by the shelf without stopping, the number of stopping customers, so that are the customer that stop in front of the shelf for a certain amount of time, demonstrating an interest on products that are on the shelf, how many of them actually interact with the product, and we can infer also the number of buyers looking at the positive interaction. In this way, we can estimate the sellout that usually is a kind of data that is not available for the final brands, but is a data that the retailer has. With all this data, we can build what is called the conversion funnel, which is depicted on your right. Basically, this was the beginning of the analytics in Grottini Lab. All of our technologies follows a common data flow. So we have data from the sensors. One important thing that I didn't mention is that to be perfectly privacy compliant, all the elaboration happens on the edge. So directly on the camera with its elaboration unit, there is no storage of images and video. So we have to use this camera in low resolution to keep the elaboration live. Then metadata are extracted, so about interaction and passing by in front of the shelf, and these data are sent to the cloud. We use an AWS infrastructure made by different services to aggregate this data, further process this data, and prepare for the presentation to give it to the final user. The presentation happens in a dashboard like this, where you have all the data about the store, so the number of people entered the store, the time spent in a category, the funnel, so how many of them stopped in a category, how many of them bought something. But also we integrate all this data with other technologies that are not computer vision related. For example, as Marina said, we have installed an RTLS system, which is an active tracking system for shopping cart and basket. In this way, we can automatically know what are the area of the store that are the most visited and the least visited. In this case, we are seeing what we call the vertical heat map. I will go a little bit. Okay, this is a vertical heat map. We get this data from the interaction. So this is what we call vertical heat map. So the intensity of the color stands for the intensity of the interaction on the product that are on the shelf. So those data comes from the interaction and the camera analysis. But there is a missing part in all this analysis that we were performing. We are not looking at the shelf. What is actually on the shelf? What are the products that I have on the shelf? So basically, we try to think how we can automate the shelf audit process. Shelf audit process is something that it's been out there for the last at least 20 years. So basically, brands send people to supermarket, to store, to look what is on the shelf. And at the beginning, this was totally manual operation. So paper and pen, and these auditors were taking note about everything that is on the shelf, the price, the competitors. Now there are many solutions out there to automate this process. We wanted to do it such as this auditor, take a single picture of the shelf, and with the artificial intelligence, we want to recognize every single product that is on the shelf. This will allow us to answer some fundamental question. For example, is the shelf layout really effective? What are the out of stock levels? How much time does the staff spend on refill operation? And but also what percentage does a planogram change impact the out of stock level? But most important, if the planogram, which is the position of the product that has been chosen, is respected when you are in the store, because usually the planogram is not respected. And also which planogram is easiest for the store staff, but also for the shopper to understand all this kind of analysis. So we designed an architecture that uses different sorts of information. So we have a mobile application and a fixed camera. Basically, both of them take a picture of the shelf. They do some kind of pre-processing to correct the perspective of the picture and to crop to the region of interest. They send this picture to the cloud. Again, it's AWS infrastructure where there are many involved services. For example, the database Redshift to store the information, the metadata about the shelf, but also the simple storage service to store the image and the artifact of the elaboration. And a containerized environment that is Elastic Container Service by AWS. This allows us to process in parallel thousands of images. Then the output is given to the client by dashboard or possibility to integrate with the API. I told you that we use different sources of information, but the use cases are really different. So we developed a fixed camera that usually we install in the shelf in front of the shelf of interest. In this case, you can do a continuous analysis. So you can take picture basically every second. But one more important aspect that we are working on is a battery-powered camera. So you don't have to wire the camera to touch the infrastructure of the store, but this camera will take picture, for example, once a day and send to the cloud, like a human will do with a mobile camera. Then we have the mobile camera application, which has a different use case. Okay, sorry for the audio. In this case, we select the store, we select the category, then we are ready to input some information about the shelf, so physical information that we use later for some insight. Then we can take a picture of the shelf, we can restrict the region of interest because maybe in the shelf there is more than in the picture there is more than one shelf, but we want to have the shelf as a single unit. Then we have the possibility, if the space is not enough, to stitch together different images or to correct the perspective of the picture in order to get the full shelf on the image. Then when everything is ready, the picture is sent to the cloud and there is the elaboration of the picture. I want to show you what is going on right now. Sorry for the Italian in this picture, but it's just a screenshot of our dashboard. Basically, we started the project in April with the brand, and from April until a couple of days ago, 2,500 audit has been done, visiting 2,500 point of sale with a total of 25,000 images processed with an average time of 3 minutes. This average time include the moment when you start the audit procedure, so when you start typing the physical dimension of the shelf, to the moment when you get the result. So there is in the middle also the time to upload the picture and all of these things. And it's not a great time, but we want to improve on this. So the process basically starts from detection of the product that are on the shelf. So we detect every single product as a common class. Then for every detection, we use a recognition network to recognize the product at the level of the EAN code. So what is important to us is to know the EAN code of the product, because the EAN code is the only unique identifier in Europe, but in US, in other countries, you have a similar way that univocally identify the product. So for the detection part, we started using a pre-trained retina network on SKU 110K dataset, which was presented here in CVPR. It works very well in a retail environment because the dataset was designed specifically for this task, for detection in densely packed scene. And in this case, we didn't reinvent the wheel, but we just fine-tuned the network with some images of our dataset. Then for the recognition phase, this is something that are already at the state of the art. We used an approach similar to FaceNet, so using a triplet loss. We extract embedding from the pictures, and we project this embedding on a common embedding space. We will have that similar images. We will have the embedding vector close together, but different images, we will have a great distance between the vectors. So basically we tested different networks as backbones to extract the feature. At the end, we selected a mobile network in order to have also a great speed in processing the image. That was enough for our accuracy purpose. As I said, the shelf is dynamic, so we couldn't use a common classification network, because as you can see from this slide, that is similar to the one showed on the talk before. We have a couple of examples here. On the left, we have the same SKU, so it's the same product with the same EAN code, but with 3 different packages that were on the shelf at the same exact moment. So these were on the shelf last summer. For the first one was for celebrating the European Cup of Football. Then the middle one for collaboration between Mars and Prime Video, and then the common one of the M&Ms. But these are very different, but represent the same object. But on the right, we can see 3 different SKU, but as you can see, the difference between them is very limited comparing the entire surface of the product. So we can have a high interclass variation, but low interclass variation. So this is something that you have to keep in mind. We start looking at the data set in the literature, but we didn't find any data set that was annotated at the level of the EAN. So we needed a fine grain annotation for our analysis. So we started collecting our own data set. We started with 20,000 different ions, also collecting the picture and the ion code, scanning the barcode of every single product with 60,000 images, and we decided to give a category 3 of the product using the GS1 category 3 index. GS1 is a non-profit organization that manages the standard like the barcode. They have an hierarchical classification on 5 levels, which we choose to give a categorization of our product using the first 2 levels. So we have the category here, where the first 2 digits refers to the first level and the last 2 digits to the second level. Then we have the ion code and the number of images for each ion, for each product. We can see again another example of the shelf that is challenging. We can have promotional material occluding part of the object, or we can have different object. Look at the M&M's packages. They are quite similar, but one of them is double in size of the other. So it is important to distinguish exactly the product, because in this case, they refer to different cluster of consumer. But if you see the package is more or less the same, and also the indication about the weight, so the 500 grams or the 200 grams usually is not visible, because here you see the package that is beautiful, stretched, but when it is on the shelf, it will be not so easy to read this information from a single picture of the shelf. Talking about the single picture of the shelf, you can see here from this example, consider that this picture comes from the latest model of smartphone. So we have great resolution, but when you go to zoom for a product that are really tiny, like pet food, that is for our experiments, one of the most challenging product in retail, I challenge you to spot the difference between this and this. These are 2 different products, but looks exactly the same. But at the end, we have to distinguish somehow this product. The outcome of the system is something like that, where you have some basic information that has been uploaded during the audit. As I said before, physical measures allow us to do some calculation about, for example, the share of shelf. So how much of the shelf is dedicated to my product? This is a question that brands always want to answer. In this case, we can also compare the situation of the shelf with the planogram. Here we see highlighted the SKUs of those of this particular brand, and we have the possibility, because it can always happen, to correct any mistakes by the system. So it's the user that can validate the audit, and eventually add some missing detection or correct the number of the detection. At the end, I wanted to show you a nice page during the training. When we were at the beginning, we had a few data, and we discovered that, for example, the nut pattern of the chocolate were confused by the network with chickpeas. So the answer is that you always need to have enough data for your algorithms. Then what's next? We are working on price detection, which is not trivial because price tag has different patterns between different stores. And sometimes you have many different numbers. So you have the price, but you also have the price referred to the weight. So you have to give an interpretation of the text. And also sometimes you have more than one facing for a single SKU, but the price tag is just one. So it's better to try to understand, to read what is in the price tag. And also the promotion material detection, which is really important. What's next? Since, as I said before, we have RTLS system in our stores, we want now to use this data that give us the common path and the most visited area of the store, the less visited, to integrate with the shelf analysis. So what we want to do is to use a mobile robot. We already are working on it, and maybe set the robot to check the area of the store with high traffic, where luckily there is something that happened on the shelf. So basically, there is no sense to check a shelf where nobody passed by. So this is what we are working on, just to give you an idea of the possibility that are in this huge field that is increasing interest in research. Thank you. And here my contact detail. Feel free to reach me out and to add me on LinkedIn or to write me an email for any question. If there are any questions, I'm here.
Have you explored to automate a product counting function? Because one of the signals usually we look at when it comes to shelf management is the velocity of the product. Which product is fast moving versus other product? And are there missing products as well? Have you explored that? If so, what kind of technology are you more leaning toward?
Basically, with this kind of technology where you identify every single product, you can do it. You can count product, but to see how the fast-moving items are going, you need a continuous evaluation of the shelf. So maybe the fixed camera is the more appropriate way. So continuously evaluating the shelf, you can see how is it changing over the time. But also with the shopper analytics, with the top view camera, you can see in real time what are the interaction with the product. So you see the fast moving product with that. Yes.
Great presentation. Thank you so much. Then for your product recognition, how much sensitive to the size of the bounding box? Like detection output. Detection bounding box can be wrong, can be bigger, can be smaller than actual product. Those two different size of bounding box.
But usually we found out that the network, the detection network is pretty much accurate, but the detection it does not affect, if it was the question, for example, the calculation of the share of shelf, if it was the question, because usually there is a small difference between the expected bounding box and the real bounding box. On the recognition, no, it doesn't affect the recognition because the network has been trained with few-shot learning. It's not a one-shot learning. So we have different model coming from the real world. So we are not using artificial images, but we collected our data set in real stores.
So you said in the beginning about the shopper customer behavior, like if they pass that area, if they interact productivity real life. My question for you is that do you know if this kind of behavior is a general, like in different areas, like in grocery area, is the behavior the same as in other areas, like bakery, different areas?
Usually we work by project, so we can have a project in different project by categories. So we studying the behavior of consumer for a category, I don't know, meat or dairies, give us an insight about the behavior in that category. Then using the sparse camera system that Marina showed before, we can also reconstruct the trip of the user. So we can also cluster the shoppers based on the category they visit. So this give us a real important insight about the behavior. So probably most of the people that visit a sequence of categories as a common behavior, we can cluster in this way the shoppers.
Thank you. Okay, so we have 3 more short talks from the challenge winners. Each one is about 5 minutes, and there will be no questions. We will do other talks, and then this will be it for today. Okay.
Hello, my name is I'm currently a research engineer at the research department of Meitaning in China. I'm glad to be here to present our work on multimodal retraining for large-scale cross-modal product retrieval. This is a technical report for the first phase solution to CPR printing into Alibaba product challenge. The other team members are Dongchuan and Cao Zhong. I will explain our work from these aspects, including introduction, retraining, fine-tuning, and the retrieval methods, and the implementation, and the results. This computation requires to record the product images from a large image pool given product titles. The challenge lies on how to effectively represent the visual and language modality independently and align the interactive. The evaluation metric is the average of recall at 5 and recall at 10. The dataset contains a very large number of text-to-image pairs, which is about 5 million. The titles are noisy and thus imposes additional challenges to align the language and the region semantics. Here are 2 examples. The left is a product of chicken wings. The keyword chicken wing is represented as Chinese pinyin. In addition, the product image also contains noise, so figures of little chicken and big star. The right one is the product of teapot. The last words, EAOSF, is actually saying free delivery using Shunhong Express. Even as a Chinese, I could hardly understand it. We adopt transformer as the building blocks to process false image in the texts and follow the idea of the grid pattern. Here is the overall framework of the method. First, VIT is used as an image encoder to extract image patch features. We use 3-bird model for different purposes. The first one is the text encoder T-ink. It independently extracts feature vector of type and aligns with the image just like clip. The second one is a fusion module called MMFuse. It's modified to have an additional cross-attention layer to fuse image features with the text features. The last one is the decoder, whose bidirectional self-attention is replaced by the carrier self-attention for image-grounded auto-regressive language generation. Most of the parameters are shared across the three-fold model. There are three stages in our method. There are general pre-training, multimodal pre-training, and fine-tuning. In general pre-training, we use ViT as the visual encoder and initialize it from Facebook to EIT. In memory pre-training, we use BirdLarge as the memory model and initialize from Google Books. To handle pinning and English mixed text, we propose a text data augmentation method and synthesize such sentences using wiki corpus. Here is an illustration. Given a sentence, we first randomly sample a few consonant words like the spam bird and then translate them into Chinese. Next, we convert Chinese words to pinyin. Finally, we replace the selected English words with the generated pinyin. In multimodal pre-training, we use the RE products dataset and pre-train the model using the three tasks of image text contrasting, image text matching, and auto-regressive language modeling. The aforementioned text data augmentation is also used in this stage. Finally, we omit the text decoder model and fine-tune the model with very small learning rates. When retrieval, we use speech vectors to costly retrieve 64 images and then finally ranking them to select the top 5 and the top 10 images by MMQs. Here is the implementation detail. We gather all features across all GPUs for ITC and ITM loss to increase equivalent byte size. We also use gradient checkpoint to enable large byte size. By applying the augmentation method and other technique skills, we achieved 75% mean recall on the test dataset and take the first place in the competition. Thanks for your attention.
Okay, we'll go on to the next one.
Hello, I'm John. My colleagues and I taught in the CPR and with this presentation, we our finance solution. The aim of this challenge is to design a system which is capable of being using text queries. The system is evaluated on the task and average over 5 and the dataset proposed to study this cross-model representation problem is a realistic large-scale dataset system of 4.1 million image caption pairs of 100,000 timeframe data. The challenge lies in the scale of data, noisy image caption pairs, and multi-link captions. Now the solution is designed joint image text embedding training with an additional fine-tuning and cleaner version of the dataset, followed by inference time techniques such as test argumentation, PPA, image text scoreization, and ensemble. The first approach we use for image text alignment is the popular key. It trains the image text and projection methods jointly on the image index data. The objective function minimizes the percent between image and text encodings. We added additional loss components to the existing objective to explicitly pull apart each image and each text caption in a batch with respect to all other images and all other text captions respectively. We will refer to this method next week. The second approach we employed is ALBERT, that introduces a contrasted loss to align the image and text representations before fusing them to cross-model attention. The loss is composed of 3 objectives: image text contrasted learning loss to align image and text in a common dimensional space,
image text matching to predict whether a pair of image and text is a match or not. Max language modeling laws that utilizes both the image and the contextual text to predict the max words through a multimodal encoder with cross-modal information. Albert uses an additional momentum distillation technique, a self-training method which learns from pseudo targets produced by momentum. As I said, the training data is noisy and contains many instances where the caption does not match the corresponding image. And here we collected some example noisy data where the caption does not describe the image completely. In order to remove such noisy symbols from the training, we split the training data into 4 mutually exclusive subsets and trained 40 models. We average the responses of these models on the unseen training set to get unbiased and modelizable predictions that we then use to filter out pairs with low similarity scores. We make use of test time limitation technique for both the image and the text as well as the performance. For images, we obtain the features over 7 inferences using round-robin augmentation. For text, we employ the easy data augmentation technique of 5 inferences by randomly selecting one augmentation among word synonym replacement, random deletion, and random word swap augmentation. Our solution is made both transformer-based and convolutional-based vision architectures, coupled with either BERT or CBERT. We trained bit-based and swing-based architecture with Albert method, and swing-based and convex architectures with P10 approach. The last column shows the record time on validation set for each single model. These models are then combined in the final sample. We use each model in the previous table to produce a similarity matrix computed as a dot product between the normalized text features and image features. We further process each matrix with a normalization procedure. So for a text, the Armax similarity score with all images is a simple way of picking the best match. But the best text to image match does not imply the same match for image to text. To take image to text similarity scores into account, we perform score normalization. And to achieve this, we iteratively scale the score with the scores with the maximum with respect to images and the maximum with respect to text. After the iterative minimization, we average all the similarity indices to weights produced as a softmax over the corresponding validation of the 10, using a temperature of 0.5. With our solution, we were able to achieve a score equal to 72.695, mean record 5 and record 10 on the test set, resulting in the second best method in the challenge. Thank you everybody for listening.
Okay, and now we have the third place as the last talk.
Hello everyone, I'm Jihan from the team. That introduces our solution for that product to much the cross-country product retrieval challenge. We made our solution at IT R, that is text recovery and ranking plus the corresponding product retrieval. At the beginning, I'd like to introduce our team. All of our members are from Solos. Solos provides global identity verification software and is brand for groups and security capabilities with our developing super app. We are contributing a year of Solos. It is developing accuracy and security. Every day, we process huge amount of features to similarity detection, the environment key needs to decrease image contents, like expense or other issues. We also focus on research about new representation, retrieval, self-supervised learning, and retrieval. We handle this challenge as it's quite similar with our scenario. We have applied the text detection to improve users' experience and gameplay, and also hope to explore the frontier of machine understanding to learn some techniques from our teams. We must give thanks to this challenge, providing a digital cost model and true reset so that we can share our new ideas. This is an overview of our content. First is our analysis. We found there are a lot of noises in the training data and the validation data. Some text captions are not well matched with the corresponding product images, such as image text error as shown on the screen. So we try to decrease the effect of noise with text errors when we design our approach. And through our review of text captions, we found some text captions containing both English and Pinyin words. We believe it will confuse the text encoding model since the meaning of some words in English and Pinyin may be quite different. For survey data itself, we can see training set contains over 4 million pairs and the data set contains 50 kilopairs of text and one corresponding image. However, the test set has 20 kilo text captions and 50 kilo images. Through our analysis, each image has at most one corresponding text. Our ranking strategy is based on this rule. Next is our approach. For the training data, there are a lot of noise text pairs. To overcome it, we train the data by models. Firstly, we train the image encoder and text encoder contrast learning model. By the training data, then we use train model predicting corresponding text image similarity. Finally, we rank the scores and judge the last 50 kilo unmatched text image pairs. Next, our embedding approach. We focus on text caption containing both English and Pinyin words. To reduce confusion, we apply individual embedding to the text encoder. Firstly, we distinguish the Pinyin part and the English part. The second for English part, we use embedding. For Pinyin part, we use Pinyin embedding as shown here. We will have to stop. This page is the key part of our approach. We use several popular vision and version models and our basic models. That is ALV and line confusion, TTL, tribute consciously learning, and XDNA. We use the official creation text encoders and region and text pairs. And with that, we find sure of the inset text, which is north, text, north. Here are all the settings for each package. For XDLF, we use main transformer-based version as backbone. We use 32 at hash size, 384 and 480. For both ALV and TCL, we use main transformer-based as backbone with 16 at hash size, 384. So we have each single model prototype each different model settings. And for each model, we individually apply record action. On the first stage, we extract features and the text features from the test set and to precise similarity between text and features. For each text, we get from 256 candidates. Next is the second stage. For each text caption and select the top 256 entries, we can create a score by action head with text and feature. And each model generates 30 kilo plus 50 kilos for matrix. And we get 8 for matrix, which are some common methods such as compare score max, score multiply, and visualization. and find a video basically most useful message. To obtain the most appropriate ways, we apply differential evolution applications for optimize. Next, the ranking strategy. We observed that each page had a most corresponding text. Possible results find some creative overheat by a lot of captions. To avoid these cases, if slightly just caused by we use research to search what's appropriate. Together, we get for each work or test else, exactly why. And the final part is our results. This page shows quantitative results. You can see we can similar scores on my dataset and test sets. Figures results for improvements on our strategies. On this page, we use some literary examples of caption, reduction, images. Finally, our conclusion, we found that applying text direction on this with achievable performance and the individual can be very helpful. Contribution to a common method with revision and the ranking fit can lead to higher score. And for products challenge itself, it's very interesting and challenging to find out the sort of technique to solve the problem. We are looking forward to product to find a next year. Thank you for listening. All for our content. If you have any questions, please feel free to connect with us.
Okay, so that's all for today. Thank you everyone for joining us. And if you have any questions, suggestions, anything, you're welcome to contact me or the other organizers. Our details are in the workshop website. And enjoy your stay at CVPR. Thank you. תודה. נפתח, חכה ונראה מה יקלט.
הכי חשוב. יש לי עוד משהו או לא?
חושב שלא.
זהו, עכשיו יש לך זמן לנו. רגע, שנייה.